Okay, so very good morning and welcome to this symposium on OpenFOAM organized by FOSSEE IIT Bombay. And I wish you a very happy new year on behalf of the entire FOSSEE team of IIT Bombay. So first, before we go ahead with the talk sessions and panel discussion and workshops, everything, let me just talk about what is FOSSEE, who we are and what we do. Okay, so FOSSEE is a project which is being developed at IIT Bombay. It is funded by the Ministry of Education, Government of India, and it is a part of the National Mission on Education through ICT. So our mission or our vision is to reach out to every nook and corner of India and uplift the education level through practical training of free and open source software. So this is the mission on which we are working. And FOSSEE mainly trains, promotes and encourages the usage of free and open source software. So now let me just briefly explain what is FOSS or FLOSS. So FOSS is free and open source software, and FLOSS is the same thing. L stands for liber. We also call it free liber open source software. Okay, so this FOSS is actually software that we can download free of cost legally because they come with GPL and BSD licenses. You can modify the code for free. We can distribute the code for free, and we can also distribute the modified version of the software. So these four aspects of free or liberty is there, which is associated with the word FOSS. So it is not that it is free of cost only. So it is free of cost, but plus the usage is free, plus the modification and distribution is also free. So this is what FOSS is. Now why FOSS? This is very important to know that why we are stressing on learning of FOSS. So this is the knowledge that if one acquires, it can be with you throughout your lifetime. So it's a kind of value addition along with your education, the mainstream education that you are receiving through your college and higher education. So this, the knowledge of FOSS is going to be there as a lifetime asset with you all. Okay, so it is a value addition for a lifetime. Why I am saying is like that, suppose you are in a premier institute today. People from the tier 2 and tier 3 colleges, they are not always exposed to software that comes with licenses that are costing lakhs of rupees. So number one, the colleges can save lakhs of rupees if they switch to FOSS. And also there is no guarantee that you will join after you pass, after you graduate. There is no guarantee that you are joining a big MNC wherein you will get the expensive licensed proprietary software for free to use. That is why the knowledge of FOSS is mandatory. For example, tomorrow you can also go for starting a startup, opening a startup, and also joining MSMEs. So then the knowledge of FOSS will be very helpful to you. That is why we stress on learning free and open source software along with the software that is being taught at your educational institutions. Okay, now let me talk about what we are doing in the FOSSEE CFD team. Okay, so mainly we are training the CFD enthusiasts on a software called OpenFOAM. We are here to talk about OpenFOAM today, talk about CFD today in the symposium, and tomorrow we will have a workshop on the advanced features of OpenFOAM. So what we do is we actually train the learners so that they come up to a level in which they are capable of generating output in terms of mini projects. For example, case studies project, for example, research migration project, like that. And in this process, they can also publish papers in renowned journals as book chapters or in conference proceedings. And this training is imparted through internships and fellowships, and also there are projects that can be taken up throughout the year. Internships and fellowships are actually programs that we offer for a particular period of time. For example, 2 to 3 months in the beginning of every semester, in the summer, in autumn and winter. But apart from that, there are programs that the learners can opt for throughout the year. We also offer workshops on basic level of OpenFOAM. We also train the faculties through the faculty development programs. We also have industry partners who interact with our interns and fellows and trains them. Okay, and I'll just come to the next slide where I'll talk about our team and whom we are associated with. Okay, and we also conduct industry academia programs as a part of the FOSSEE CFD activities, because learning or upliftment of a subject. For example, we are all here to talk about CFD. So it is not like that if we confine ourselves within the academia, the knowledge will be fulfilled. So what we do is we have many industry partners with whom we collaborate. They actually talk about the latest techniques or the latest problems that they are facing in the corporate. So they actually also train the students, our interns and fellows. Okay, now our team. So we have a team who are working at IIT Bombay, and we are directly associated as professors from IIT Bombay. But we also have faculty partners who are not from IIT Bombay. They are from institutes which are outside IIT Bombay. So we have 17 such professors who are working with us as faculty partners. They train the students, the interns and fellows of FOSSEE, and they also take sessions in the workshop. We also have advisory board members who are from the industry. So we have almost 17 people, 17 or 18 people are there now. So they are all from the CFD industry who are working with us as partners. So today we have some of the faculty partners here joined with us, and in the panel discussion we will all interact with them. So with this I'll conclude my talk. So today we are, after my talk, we are actually starting the talk sessions by the esteemed professors of IIT Bombay, and I welcome you all once again to this symposium. So I would request Professor Chandan Bose now to briefly talk about the FOSSEE activities that we are taking up at present and our future plans. Thanks a lot.
Hello everyone, I hope I'm audible. So let me introduce me very briefly for those who doesn't know me. I'm Chandan Bose. I'm an assistant professor of aerospace engineering in University of Birmingham, UK, and also I'm a visiting faculty here, particularly with the role of leading the CFD activities OpenFOAM project of FOSSEE. So I just wanted to follow up the discussion we were having on the role of FOSSEE on particularly highlighting some of the activities that we are currently focusing so that we can ask some feedback from the IITB community. So what should we continue and what we should add as a new activity, and what is the basic impact of this activity so that we can reach out to more and more OpenFOAM or open source CFD enthusiasts. And the other part is, should we keep it confined only with OpenFOAM or be open with other open source tools for CFD and other things. So just I won't take much time because I think we started late, and apologies for that to everybody on behalf of the FOSSEE team. We have already known the teams here, so I am basically, it's my honor to lead this activity in the India, because I always feel that this is one of its kind in terms of its project for promoting open source tools and codes for particularly computational fluid dynamics education. I'm working with Professor Manushita Bose and Professor Siva from IIT Bombay, and also Professor Janani is always in support of us for promoting these activities. And we have, of course, Ms. Pyle and other FOSSEE project managers, and we have a wonderful team of research assistants who are working full-time and part-time in this. Particularly, we have two different activities. One is promoting the education of OpenFOAM in terms of users and development, but on the other hand, we also are interested in a novel development of graphical user interface. So we basically have two different teams working mostly on OpenFOAM activities, developing the code and promoting its users for different application. On the other hand, we are also trying to develop a graphical user interface, which is, we feel there is a need, particularly when we interface it with industrial partners, because they would want a graphical user interface. And there are different other efforts going on throughout globally, and we are trying to just contribute to that, if possible, from FOSSEE team. So I just want to give some basic level of statistics on, in 2025, what are the different activities that we carried out throughout this project. So we started with semester-long internship, which was quite demanding in terms of application, although we had a strict screening process, but we got a lot of applications, and ultimately we had 10 projects in semester-long internship for OpenFOAM codes and development, and 3 projects for graphical user interface development. Then we had summer fellowship. There also we had 11 plus 3, total 14 summer fellowship projects, and all these projects are updated in the FOSSEE OpenFOAM website as case studies or research migration project. And also we ended the year with some autumn and winter fellowships, where there are some ongoing projects with 9 and 2, total 11 projects, which will be submitted very soon in January and will be updated in the website. Apart from that, we also support outside these fellowships. We encourage people to learn OpenFOAM and work with us and submit case studies, project and research migration project, particularly with a major focus to validate the code and verify the code with existing experimental results and literature. And we have also ongoing lab migration project with different private engineering colleges, where they're actually adopting OpenFOAM for their CFD labs. And we carried out basic level of workshop on OpenFOAM at the start of 2025, and tomorrow we are having intermediate to advanced level of workshop. We had a faculty development program, and for the first time we had an industry readiness workshop, where we invited different industry CFD engineers to come and talk to us what kind of application they would like OpenFOAM to be used, and how we can increase the employability of Indian budding engineers who are learning CFD and OpenFOAM. And we try to understand how open source code, how much demand it is creating in the Indian industry sector in that sense. So basically, these are some of the clips that I've got. We promoted it over LinkedIn, and I just collected some of the photos. Professor Kannan, along with the team, also did some podcast about OpenFOAM, just to make it more visible in terms of industrial sector. And yes, so just wanted to highlight, I just put all the topics on ChatGPT and tried to understand what are the different topics that we have covered in our case studies and things. It's not perfect, but I just wanted to get a glimpse of areas, and it's quite encouraging to see that we have actually covered different aspects. It's quite diverse. Particularly, I guide projects on aerodynamics and fluid structure interaction. We have other faculty partners who guide project on multi-phase flow, heat transfer, and also different type of application-oriented engineering, as well as numerical methods and MES. So it is quite encouraging to see that in terms of topics that the students are being offered are quite diverse, and not only that, in terms of participation from different institutes in India are also quite diverse, not only from premier institutes like IIT and IT, lot of smaller engineering colleges people, they come and present their work, as well as we have a very good diversity in terms of males and females interns who come to us, and which is quite encouraging to see. So as I already said, that in future we are going to continue the development of activities of intermediate to advanced level of training, which is the way to go, because we have done for many years basic level of trainings, but now we have to go towards the developmental side. And of course the graphical user interface in another thing, and there's some discussion that we are thinking along with all our faculty partners, can we create a MOOC on national NPTEL kind of level, so that it remains a resource for all the students. And we now have gathered a lot of materials that we have offered workshops for years, but can we make it a national level resource for the students? And it cannot be done by one people, so we need to come up all together. All the partners and faculty partners can come together, and from their expertise they can create this. So we hope to go towards intermediate to advanced level, and we want to go industry readiness workshop 2.0 in 2026, and also we want to release and publicize more the GUI Venturial that is getting developed within the FOSSEE CFD project. Now there is not much of a time, but I want to just highlight some of the challenges. If there are time permits, I would like to discuss as part of also the panel discussion that I just discussed with Professor Siva, that how can we give a little bit more resource to the interns rather than just some old workstation, because they struggle a lot going beyond their own laptop. So if we can get some resource from NSM or other national projects for particularly dedicated for interns, that will be quite good. And then of course what I felt over the last 2 years is the quality of the selected interns and the quality of the output that we generate. One is the number, that how many case studies we are generating, but other is the quality, whether they are really of well quality to publicize in the global level, or to tell the world that we are doing this kind of work. So, and how can we actually get more encouraged or more good quality students, etc. And of course one more important, which is it's a high time to do it, is the version control of whatever we have already done for the last 10 years, let's say, for whole throughout this FOSSEE project. We have 200 plus case studies and codes and everything, but most of them does not work with the newer version of the code. So how do we make it at par with the newer version of OpenFOAM, which people can use directly? And for example, this kind of Venturial kind of new development, how can we track this development as part of our evidence of the project outputs? With these notes, which we can discuss again at the end of the day, I would welcome our speakers for the day, and I'm looking forward to listen to their talks and activities. Thank you. You have the list, right? Oh, yeah.
So thank you so much, Professor Chandan. So with this, we can go ahead with the talk sessions, beginning with Professor Shiva's talk. So welcome, Professor Shiva. Professor Shiva is a faculty at Mechanical Engineering Department of IIT Bombay, and we all welcome him into this symposium.
Yeah, still? Okay. 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 Can I start? All right, good. Okay, so when I was invited to this talk, I didn't know how much I should speak because I titled the talk OpenFOAM Accelerating Research in Academia and Industry. But before that, I'll just give you a brief history of my association with OpenFOAM. And it goes back, and I just recounted it, goes back 2 decades, more than 2 decades now. So I feel really old. I just want to quickly show you one snapshot from the second OpenFOAM workshop in Zagreb, Croatia, 2006 Jan. That's, if you were to clock back, it's almost 20 years. Since then, I'm somewhere in the crowd. I see my PhD advisor over here. And that's the journey with OpenFOAM. We started back in the day, a ragtag set of people. No, you don't need to applaud anything. It just makes me feel old because there are people in this room who are probably born after that date, right? So there are people in the room who have been born after that date. So my association with OpenFOAM goes back a really, really long way. So I am pleasantly happy to see how it has grown, how it has been adopted not only in the West but also here, and increasingly both in academia and industry. So my association with OpenFOAM started with working on a PhD problem, and at that time we were, I mean, back in 2004, 2005, if you had to solve a CFD problem, you had to write your own code from scratch, okay, from scratch. So that's a big challenge. You had some utilities, you had some libraries, you could, call some math libraries to solve some linear algebra problem, and all those things you could do. But more or less, if you had to solve some sort of problem which didn't exist in commercial solvers, you had to write things from scratch, and that was very, very daunting. Daunting, especially because you never knew whether you'll be able to complete your PhD in time, right? And obviously, can you then start looking at grander challenge problems, bigger problems, etc. So one of the first things. So by the way, I'm not going to bore you with any equations or any bits of code in this talk. I took some inspiration from the preface of Stephen Hawking's book, Brief History of Time, where he says that for every equation you put in a book, you lose half the viewers, right, or half the readers. So I have consciously stayed away from putting equations here in this talk. But this was the first problem that I started working with when I began my journey with OpenFOAM. And the task was, we were trying to model what is called as non-equilibrium phase change in fuel injectors. And this was a real problem in the sense this is 2005, 2006. The world was interested in, obviously at that point of time, and it still is interested in increasing the efficiency of gasoline engines. And one of the technologies that they were experimenting with, and the bigger automotive manufacturers they were experimenting with, was something called as GDIs, or gasoline direct injection. So if you're aware of how an internal combustion engine works, especially standard petrol engine, you realize that you inject the fuel close to what is called a stop dead center, or when the pressure is at the highest point, and then combustion takes over and energy is produced, so on and so forth, standard IC engine cycle. But one of the problems with port fuel injection is that the fuel does not mix properly inside the combustion chamber. There is an issue of wall wetting with the inside the piston cylinder arrangement, and there is wasted fuel, unburned fuel, which sort of escapes in the cycle, right? And so that obviously drops down your fuel efficiency. So one of the thought the engineers had was, okay, instead of injecting the fuel at top dead center, let's now inject it at close to bottom dead center, or when the full suction stroke is done. Okay. Now the problem with that is that you have pressures in the combustion chamber below ambient pressure because the suction stroke is done. So as you're putting in the fuel, because the pressure is so low, will start vaporizing, right? It will start vaporizing, and there's a danger of vapor lock, right? So that's one thing we need to understand. The second thing is, how do we model this? How do we model this fuel injection process? Because the pressures are going so low, you're going to start seeing vaporization within the fuel injector itself. So typically in normal fuel injectors, you have full liquid fuel going, and the vaporization takes place only inside the combustion chamber. But now, because the back pressure is so low, you'll start probably seeing vaporization within the fuel injector nozzle itself. So how do you design this nozzle? How do I understand the physics of it? And to add to the challenge, this is not a single species liquid. Petrol contains several components. It has octane, it has lighter fractions, heavier fractions. It's generally a mix of many things. So it's essentially a multi-component hydrocarbon. Okay, so multi-component hydrocarbon, but as a single species. Then the second problem is, how long does this injection take place? So typical car runs at about if you're idling the engine, it's about 800 RPM. If you're driving it regularly with normal load on the engine, not climbing up a hill, etc., it's about 1500 RPM, 1200 to 1500 RPM, depending on how your engine is configured. Your injection time is a small fraction of that cycle, right? So 1500 RPM typically means 4-stroke cycle. So divide by 2, and then you can figure out how much time it takes for one particular full cycle. Injection is a small fraction of that. So it's really, really small amount of time. It's a few milliseconds, barely few milliseconds, or it's almost few tens of microseconds where the injection actually takes place. Now in that time, the fuel, when it is vaporizing, what we think as engineers is that the moment a thermodynamic state is reached, right, pressure, temperature, all the other properties will reach there immediately. But that is equilibrium thermodynamics. But in that short period of time, there is no equilibrium, right? So there is some finite lag for which this needs to come in. So now you have to model the phase change with thermodynamic non-equilibrium. Now think about the complexity of the physics in it, right? Now I have to model multiple species or model some surrogate fuel. I have to model the non-equilibrium, and then I have to take care of real world injector geometries. I cannot just do this in a straight tube and say, hey, problem is done. This is a real world. This, by the way, is an actual fuel injector from Bosch which goes into an operational GM engine, right? So think about the complexity of the problem, and you don't have 15 years to develop this. I mean, if I had taken 15 years to do it, writing code from scratch to model this, by then EVs would have come and this is gone in history, right? I mean, you have to do this cycle. What really helped us is OpenFOAM. Okay, OpenFOAM was in its early days. In fact, it was foam till 2004, and then they open sourced it in 2004. There was a small community, primarily out of Imperial College, Henry Weller, Herv Yasak, and others. Then Herv got a faculty position at Zagreb. He moved there. He worked with few people. We were one of the few people in, I was a student in the United States at that time. We were one of the few people who started working there with them. And we decided, let's try this modular approach and to see if we can develop something quickly enough and test it for real world engineering problems. And I was fortunate, things worked. I mean, with research, nothing is guaranteed, but things worked. We were able to develop this quickly enough. And within a period of about 3.5 to 4 years, we were actually able to give a validated code for engineering sort of calculations to General Motors. So much so that in their production cars from 2008 onwards, they actually used this model inside to model the fuel injectors, design GDI type of engines. Similarly, the same model was used to model non-equilibrium flows for jet fuel, Jet A and JP8, and this was used for Pratt & Whitney's engines by United Tech, right? So the modularity of this code helped us to sort of really accelerate a lot of the complex industrial type calculations that we need to do, okay? And that's the story I'm going to tell you today. So what sort of different problems that we have attacked in the last couple of decades. I can't talk about all of it because some of it is under IP and I can't talk about it in open. Some of it is ongoing. Some of it there were failures too. I'm not saying that everything is hunky-dory, right? You can't have everything succeed all the time. So this was one of the first problems that we worked on. Then as I got to IIT Bombay, we started looking at fundamentals of jets and cross flows. And this was sort of important for us, looking at the fundamental dynamics of how jets break up in cross flow. This is a complete multi-phase flow problem with Rance type closures for turbulence. And we wanted to study the characteristics of the breakup of this jet. And the reason was that, again, it was an industry-driven problem of trying to look at land-based gas turbines, fuel injection in land-based gas turbines. So you're injecting liquid fuel into the combustors of gas turbines. There was a cross flow. It would break up. You wanted to see how these breakup modes would occur. Again, to look at fundamental, breakup characteristic, breakup, then mixing efficiency, so on and so forth. This is again a similar problem to the jet and cross flow problem. Here we used a volume of fluid sort of approach where we were not explicitly tracking each and every phase, right? So because we were using a volume of fluid approach, we had to resolve a lot of features, right? And that means it was computationally very, very expensive for us. So we could only do basic fundamental studies with it and then come up with sort of better correlations in terms of atomization models and breakup models. The next problem where this helped us was over here. So this is basically an Lagrangian Eulerian type of problem where you again have, in this case, injection of water into a cross flow of superheated steam. And the water sort of breaks up into many, many small droplets and then finally eventually will vaporize. Now you will ask, what is the purpose of this? So this is used as a control mechanism in thermal power plants, right? So the idea of thermal power plants is that you generate a lot of heat. The heat is used to produce large amounts of steam. The steam goes and drives a turbine, produces power. But when the superheated steam is produced, one needs to modulate and control the temperature of the superheated steam because the combustion process will generate steam at extremely high temperatures. But when the steam actually goes through the system and hits the turbine, you need to have some sort of control at what temperature the steam is hitting the turbine. Because if it hits at extremely high temperatures, you will have material destruction of the turbine blades, which are very, very expensive. So the way, how do you control high temperature steam? How do I modulate the temperature? The way is that I inject water, right? So you inject water, basic thermodynamics kicks in, first law kicks in. The water vaporizes, takes away energy from the steam, and then you have this delicate balance. But here's the challenge again. I need to understand how the breakup of this water takes place, the atomization of this water takes place, how it vaporizes, how much the temperature drop is there, okay, and is there any residual water left? Because imagine I inject, if I under inject water, I am not going to cool the steam to the desired temperature. If I over inject water, I not only waste energy by overcooling the steam, but there is a strong possibility that not all of the water will vaporize, and then you have a bullet. You literally have a bullet because water is 1,000 times more dense than steam almost, and it's going to go and hit the turbine blade with that much momentum, right? So you're going to cause further damage. So you have to understand this entire process and you have to model this. And this is not easy. I cannot resolve. Remember, the size of this pipe is about a meter, right? You go to a large 500, 600 megawatt steam power plant, this pipe is about a meter in diameter. Your droplets are micron size. I cannot fundamentally resolve each and every droplet. It's computationally, you give me, forget the supercomputer sitting here, you give me the world's fastest supercomputer, yet it's not a tractable problem, and it's not worthwhile throwing that much energy into a problem because the energy that is being produced by the steam power plant is probably not enough to pay for that computation at that point of time, right? So how do you solve it? You solve it using arbitrary Lagrangian Eulerian. So you model these droplets as Lagrangian particles, Lagrangian parcels in the cross flow. You put in correlations. I will again not go to the math. If you want to talk about the math, you can come. There's an entire paper, there's an entire report about it. But again, we were able to do these calculations within a year. We were able to suggest to the company which is producing the steam power control valves, hey, this is the prediction from CFD. We validated it against experiments. We did some fine tuning. And then we say, okay, here are the atomizer design changes you can make to make this mixing more efficient. We did a similar problem for something called as pulse detonation engines for a ballistic slab. This is another interesting problem which we used volume of fluids for. This is steel converter simulations. So a steel converter, this is for a Japanese steel company. So steel converter is basically where you have molten steel and you're hitting this molten steel with extremely high velocity compressible air jets. The reason is that you want to agitate this molten steel so that all the slag and the impurities in the steel sort of comes up in the surface and you take it off. Challenge here, molten steel, 7,000 to 1 density ratio, compressible air, 1 kg per meter cube, steel 7,000 kg per meter, 7,200. It's 7,000 kg per meter cube steel is sloshing around, model it accurately, and then to see how these injectors can be placed optimally so that you have reasonable sloshing, reasonable mixing, so that the reasonable slag extraction can take place. Magnetohydrodynamics. So this is the test blanket module for the ITER fusion reactor, and you can see the scale of the human being here. So there's a breeder section here. So one of the things the fusion reactor needs as a fuel is deuterium and tritium. Deuterium is not plentifully available. Deuterium and tritium needs to be created through a process, and it's created in a process called TBM or in a test blanket module. So what is a test blanket module? It basically has flowing lead lithium alloy. Okay, lead, one of the heaviest metals known to mankind, lithium very, very light, mixed together, eutectic alloy is flowing through. It's a magnetohydrodynamic fluid. And in that, helium, so you basically are having a nuclear reaction which is producing deuterium, and byproduct of that is helium. And there's a possibility of a helium ingress in that, right? So this is being done in a very, very strong magnetic field. So we have to model this as a magnetohydrodynamic fluid, right? So we were trying to understand the physics of the magnetohydrodynamic flow at extremely high Hartmann numbers in this TBM module. Also again in OpenFOAM. Biological flows. So we talked about a lot of industry. Biological flows. So when the pandemic hit, there was a lot of CFD being used to study different types of flow dynamics. One of the theories, a doctor came to me and said, can we study the the flow characteristics inside the nasal passage, right? Because one of the mechanisms of the vector was that these pathogens would go through your nasal passage, and some of them would get sort of stuck in the nasal passage and some would go inside. There are ways to sort of rinse it out, but to understand that process, we had to understand the flow dynamics within this nasal passage. So we actually took, if you look very closely, that's my nose. That's actually my nose. So I took my MRI, reconstructed the mesh, and put it up there and tried to study the flow dynamics inside it. So this is a project which didn't take off too much because the science of the rinsing off the pathogens, etc., was not really sound. But the idea was that we wanted to study the fluid mechanics, right? While it didn't go anywhere, it was a hobby project, but it was fun to do it. The fact was that we were able to take such a complicated geometry, right? I mean, think about the complicated geometry of the nose, especially my nose, very complicated. And we were able to model it all the way up to the back of the esophagus right here. So this is the green part is the entire cavity. And we were able to sort of model that. This was another interesting project we did with doctors at the KEM hospital in Mumbai. This was trying to look at blood flow, especially in portal vein system, and mostly for patients with liver cirrhosis. Now, the issue with liver cirrhosis is that the portal vein system sort of terminates towards the liver, okay? And there are a bunch of capillaries which then go in into the next part of the digestive system. Those get completely clogged in patients with cirrhosis. So there are lots and lots of clots, etc. So sort of pressure builds up over here. And once the pressure builds up, what happens is that some capillaries will burst somewhere, usually in the digestive tract, and usually the patient sort of bleeds out through the digestive system. That's typically what happens to these patients. So the surgeon had an idea that, hey, if I can put a shunt to relieve the pressure, right? If you relieve the pressure, then you might not end up with those capillaries bursting, etc., and bleeding out. But where do you put the shunt? How do you put the shunt? So for that, you need to understand the flow mechanism in this portal vein system. This is actually, again, this is not my portal vein. I have a perfectly healthy liver, thanks to everything. But this is from a patient who was unwell, and we were able to sort of look at this the flow dynamics within the portal vein system, and also make sort of analysis of where the pressure builds up, and that sort of can guide the surgeon to where can he or she put a shunt in the system to relieve the pressure. So what I want to drive from this talk is that you can see the diverse ways where we can apply this technology, right? CFD can be applied in many places, but the fact that somebody like me whose forte is just modeling, right? I'm not a doctor. I don't know anything about portal vein system. I am not a metallurgist. I don't know anything about molten steel. Okay, I'm a mechanical engineer. I do know something about power plants. I'm not a nuclear scientist. I don't know anything about TPM. But the fact that my strength is, I always say, give me a PDE, I will solve it for you numerically, not analytically, numerically. And I can do it very quickly using a toolkit like OpenFOAM. That's the beauty of it. And I can solve extremely complex problems using things at extremely large scales. Now, I'll show you a couple of more problems which we have not solved using OpenFOAM, but hopefully someday I will want to solve it using OpenFOAM. This was done using some other standalone codes. This is a problem of the 2004 Indian Ocean tsunami, right? So looking at the tsunami origin, how the waves spread. I'll show you an animation of this in a bit. And then once the tsunami takes place, this is the coastal inundation. So the wave actually comes and there are some buildings, etc. How does it flood the coast? So these are sort of the same problems, but sort of de-linked in certain ways. We are using different techniques to solve this. We are using different numerical methods to solve this. My hope is that someday these techniques, so the other advantage about OpenFOAM is that, as Professor Bose said, and Ms. Payal said, it's open source. We can keep modifying this code. We can keep adding stuff ourselves. So we would like to add these numerical techniques into a toolkit like this so that you can actually sort of utilize it. Okay. So I'll just quickly show you some animations before I close the talk. Yeah, so this is the, is this loading up? Yeah, there you go. Yeah, you can see this is the 2004 Indian Ocean tsunami. You can see the wave arriving. You can actually see the wave go all the way to Africa. People measured the tsunami all the way in Africa. While the majority of the damage was in Sri Lanka, eastern coast of India, Thailand, and Indonesia, the measurements happened all the way here. In fact, they even measured the tsunami wave in Goa, which is on the western coast of India. I'd like to also show you, this is the injection of water in this the steam control valve. By the way, all this is validated stuff, okay? So it's not just carefully fudged data or CFD. This was another interesting project of an agitator in a food processing plant. So there was this agro industry which came, said that they had this different ingredients which would go into this large agitator and they had to mix it. And they wanted to optimize the agitator arms, where to sort of place it, right? So that you could mix it most efficiently with least amount of energy. So this was a problem. And this exploited everything, AMR, moving reference frame, so on and so forth, right? And lastly, I would like to show you, this was the steel simulation. You can see the sloshing of the steel, which is happening over here, the liquid steel. That's the steel air interface. Yeah, so what are we doing now further with OpenFOAM? The current projects that we're working on modeling ALD, atomic layer deposition. This is mainly for sort of semiconductor manufacturing of semiconductor chips. The other thing that we are looking at is modeling electrolysis for alkaline electrolyzers. This is with the hydrogen economy, right? So there's energy which is being generated either through green sources like wind and solar, even gray through thermal and hydro plants. But if you want to transform it to the hydrogen economy, you have to generate hydrogen, and it's done through the process of electrolysis. So where we are looking at trying to optimize the shape of electrodes using CFD simulation. Okay, with that, thank you. I'm open for a few questions if there's time. Yeah. Yeah. Okay, very good. So for the VOF solvers, it's basically interFOAM. Okay. The non-equilibrium phase change is a custom solver which we developed on our own. It's not part of the standard release. We have not shared it publicly, but on request we can share it. There's no problem with that because it was sort of IP back in 2009, 2010, but now we are open to sharing it. We have used that solver now to model other things also, including modeling non-equilibrium phase change of ammonia mixtures, modeling refrigerants. So, but we are happy to share that.
And may I ask also what kind of meshing tools that you have used?
Okay, good. So meshing tools is a big challenge in OpenFOAM, as you realize. Generating good meshes is the art to so if you have fairly clean geometries and regular geometries, even complicated shapes but fairly clean watertight STL meshes, we typically rely on block mesh and SnappyX. But if it is little worse than that and where we need some geometry cleanup as well, Gmesh is my go-to.
Basically, the most complicated there was I think the Vine.
Yes, that was block mesh and SnappyX mesh.
Okay.
Block mesh and SnappyX
Nice.
mesh. So actually that looks complicated, but it's not that complicated. It's not that complicated, to be honest. Including the nose. It looks complicated, but it's not that complicated to generate that mesh. Anybody else?
I don't think they have more. Do you have any more questions? Anybody?
Yeah, I'll be back in the afternoon, so if there are more questions, you can definitely ask me then. All right, thank you.
Yeah.
Thank you.
Thank you so much, Professor Shiva. Thanks a lot. So I will just request Ms. Usha to please come. She is our senior project manager. Just Usha, if you can just give him the token of appreciation. For this I call you. Thank you so much, Professor Shiva. So going ahead with the talk sessions. So next I would request Professor Rochish Thaukar to please, sorry. I'm really sorry. Really sorry. Okay, so I would request Professor Vishwanathan to please come here and kindly present your talk. Professor Vishwanathan is a professor at MEMS, IIT Bombay. I hope most of you know him.
Okay, so first of all, thank you very much for So it will show like that, is it? Okay. Okay. Yeah. So I also, started my PhD where I was working on metallurgical processes. So at that time, again, I was, as Professor Shiva was telling, I was doing my own code because most of the commercial code was not suitable, or it was not flexible enough to model many of the metallurgical processes. Okay. And then once I joined IIT Bombay last 15 years or so, I can see that OpenFOAM, I could use it because it is more flexible and you can do your own things, because when you want to put your own physics, you can do all those things. So that is what made me get into OpenFOAM. And so primarily I will be able to talk why I am using OpenFOAM. If you ask me more about how I am, or our group is using OpenFOAM, my students will be able to tell better than me. So because most of the time I want the physics, and that is what is my expertise, and I tell them, and then they know how to do it and all those things. Most of the time that's what happens. So just to tell you, we also have a center of excellence in steel technology, and we collaborate with all major steel plants in India, and we do a lot of process models for them. So I'll give you some 3 examples just to tell you why we use OpenFOAM. So metallurgical processes are very huge. I mean, just to tell you, I will give an example of blast furnace. It can produce 10,000 tons of iron, liquid iron in a day. So the furnace will be 100-meter high and 10-meter diameter, and it's very high temperature. You put rock from the top and you get liquid metal from the bottom. So the complexity wise, in terms of number of phases, the reactions happen, all those things are what makes these systems very interesting. And the other thing is, quite often when it comes to large, such complex system, people tend to do some few experiments in the lab. They may simulate or try to understand one particular aspect, and then they get biased by that and try to explain the whole process using that particular. So in some sense, when it comes to such large complex system, I believe modeling is a tool where we can integrate all those knowledge and then try to get a comprehensive model or simulation for the whole system. So that's why I have shown the the blind man and the elephant, where each one is trying to say what an elephant is. So that's the way I believe modeling can help. And so that is what we try to do in our group. So just to tell you about blast furnace, because as I told you, why we use is what I wanted to talk about. So just to tell you what a blast furnace is. So furnace, as I told you, it can produce around 10,000 tons of liquid metal, and once it starts operating, it will operate without break for 30 years because you cannot stop it. Okay. So they charge what is the iron ore. Okay. They come in different shapes and all those things. I will not go into the details. And then the other important ingredient is what is known as coke. It's a carbon. It is made out of coal, and actually they charge it in the form of layers. And again, the shape and all those things are very important for them. And the coke is a bigger size, and the iron ore is a smaller size. Why I am talking about size is, the operator actually wants to control the gas flow through the, the operator wants more gas to flow through the center, and similarly more gas also the operator wants it to flow through the side walls. Otherwise there are issues, there will be some dust will come and accumulate, and that is going to create problems. So hence the operator wants to control this layer structure. And then what happens? Lot of chemical reactions happen. And the other interesting thing which happens is the iron ore that get reduced and then it becomes pasty. And then that will block, because the gas is being injected, hot blast is being injected, and that burns here, and the temperature here will be around 2100 degrees Celsius. And that hot gas is going up, and that is what makes the whole thing happen. So what happens, the iron ore layer, which becomes iron by the time it comes here, it becomes a pasty one, and the porosity comes down. So because of that, only the coke is the one which allows the gas. So what happens, the gas comes like this, and then actually it distributes the whole gas uniformly through the whole furnace. So the operator wants to know, quite often it's very difficult to put any probes inside, because it's very difficult. There are few experiments which have been done, otherwise most of the probes are on the wall to know what is the state of the furnace. So modeling that way helps, and they would like to know, for example, what will be the location of this cozy zone, because that is going to affect the pressure drop, and what is the quality of the metal coming out, and all those things. So this is a system we wanted to simulate the whole blast furnace, and this actually we did it for Tata Steel. So one of the challenges here is typically, in a typical fluid flow problem where heat transfer is also involved, you first solve the fluid flow, then you solve the heat transfer, because quite often the fluid flow will affect the heat transfer, but not that much on the other way, and that's the way we always do it that way. But that is not the here what happens, for example, we use, for example, to produce 1 ton of iron, we use 500 kg of carbon. All this 500 kg of carbon, it becomes gas by the time so basically you put 1 ton of gas here, it will become 2 ton at the top. That means the amount of solid, that means the generation terms are so large that these equations are highly coupled. It's not that you only solve the fluid flow and not the other things. They are all highly coupled, and that is what makes the whole problem very complex. And so people have tried to, they have never tried any of the commercial CFD. Only they will study only the fluid flow, aerodynamics in blast furnace, but not the comprehensive. Those tried, they have their own codes. For example, Japan they have, Europe, and we also tried ourselves in India. But then we understood, when it comes to delivery, or when a steel plant wants to use it, it was not efficient, it was not robust enough, and all those things. That is the time we started thinking of OpenFOAM, where we could put all these physics in a more compact form, and parallelization, all those things we could do. And that is the reason we actually went for OpenFOAM, where, as I was telling you, flexibility, and you can put your own partial differential equation. That's the other advantage. So you want to put your own physics, which is not different from the traditional equations which is available. Again, it becomes very difficult. That we could do. The other thing is, of course, Ms. Payal was also talking about, industries license fee every year they have to pay to any of this commercial, and that very much is advantageous. And what we do is we also customize this, the whole thing can be made into a, if I can say, executable file, and the person who uses this doesn't have to know CFD or any of those things. It is customized to a particular furnace, so that they can try different operating conditions and all those things. So it makes it much more easier for plants to use it. So we did develop, of course, it's not that with IIT Bombay there was also a company called Tridiagonal Solution, a Pune based CFD based company. So we collaborated with them with Tata Steel, and we had developed a simulator called BlastSim, and the whole thing is in OpenFOAM. So I will not go into the details of what it is, etc., but I can just tell you, you can see these are some of the different models. As I was telling you, this layer structure needs to be captured. There are again challenges because the the layer structure, coke layer is there, ore layer is there, and as they come down, the layer structure more or less becomes intact. So now if you try to simulate the whole thing, the diffusion comes into the picture, the false diffusion, and they start mixing, and once they start mixing, that is going to affect your gas flow. So there were challenges. Many of these challenges we could actually to some extent we could do it. Still we are looking at some of these challenges, because what happens, these layers, actually each layer will be at different temperature. At present we are having only a temperature for solid, temperature for gas, temperature for liquid. There is a liquid here, so there is also a flow liquid. So at present we have only 3 temperatures. Now we are attempting to look at the temperature of the ore layer separately and temperature of the coke layer separately. The other thing is, actually the whole process is not actually a steady state process, because you are charging layers, it can only reach a periodic steady state. But at present what we have done is, for heat transfer and mass transfer, etc., we have actually mixed those layers, though layers are there only for the gas flow, so that we can predict the more gas at the center or at the periphery, etc. But when it comes to heat transfer, etc., it is kind of, we are mixing those layers. So it's a kind of a pseudo steady state model is what we are attempting. No one has attempted this. People are still working on it, how to predict the layers, temperatures and all those things. We are still working on it. So again, we have to modify equations. For example, what happens, again, we cannot use very complicated granular flow models, etc., because the whole system itself is complex, that if you put each one of them complex, it will take so much time. So at the end, the industry wants in 2 hours, they want a solution. So hence we use relatively simple models. But at the same time, for example, this coke layers, the layers come, the iron has become liquid, but the coke layer, it forms a heap at the center, and this heap needs to be captured because that is going to affect the process. So there are already some simplification available. In a potential flow model, you put an extra factor, and this factor can be adjusted so that it forms a heap and all those things. So again, these are kind of one's own physics which can be very easily incorporated in OpenFOAM. So I will not again, so these are, for example, some of the simulation where there are actually 3 types of layers, blue and the green and the red. So how these layers, they advect downwards, and that is going to affect the flow of, again I am not going into the flow equations and all those things. And the other point is, of course, it's not a compressible flow, but at the same time we need to make sure that the density variation is captured, because temperature is varying from almost 2400 Kelvin to 400 Kelvin. So the variation in pressure and temperature, that resulting in density of gas, that needs to be captured, but not really the compressible flow. So these are, as you can see, for example, as I was talking about, the gas which is going from here and getting distributed, as you can see, it takes a turn, and then actually even through these layers it actually takes a zigzag path. Again, I don't want to get into the, and lot of reaction, more than 40 chemical reactions are there inside this. Okay, so lot of source terms. So each of these reactions, again, solid gas reaction, there are a lot of models available. Just to tell you, for example, if you iron ore is what is known as hematite, which is Fe2O3, it becomes Fe3O4. then it becomes FeO, then it becomes iron. So if you take a pellet, there will be 4 layers. The outermost layer will be iron, inside that will be FeO, inside that will be Fe3O4, then Fe2O3. So all these things needs to be put in. So of course we have not done any multi-scale. In principle, that is the next step one can think of. We have put some analytical approximations so that these can be captured. So all those things are incorporated. That's what I was telling you. Most of the time I spend time in the physics rather than how to use the OpenFOAM, that my students and my collaborators do it. And the other thing is they also have to work out how this whole, because so many loops and how the local convergence. So different things has to be tried out so that, for as I was talking about this, the zone where the gas actually takes the turn, that depends on what is known as the start of the melting and end of the melting. That is the place where actually it becomes softened and the permeability comes down. So these, for example, steel plants do experiments depending on the raw material. These start of melting and end of melting will change. So once they change, then we can actually simulate and see whether it will go down or up or what is the shape. All those things can be predicted. So these are some of the validations, etc. And again, one can actually measure the pressure profile at the walls. So that is one of the ways they also know where the zone where gas actually takes the turn. So they have those measurements. We have validated with those pressure measurements so that we know that whatever is available in the plant, we can do that. And then so many things, and you can try different operating parameters. For example, this is one of the parameters they use, flame temperature. So as you change, what happens? You can see that the location is changing. Many of those things is important because that is going to affect the quality of the product which they make. And at present, Tata Steel is using this because as Professor Shiva was talking about, now they all want to inject hydrogen because they want to reduce the carbon. So now they want to inject hydrogen here. They have already done some experiments. They want to inject hydrogen and somewhere in the shaft. So now Tata Steel is actually using this model by putting some additions here so that they can know what happens when you do some of these. One of the problems I will tell you is if you inject hydrogen here, it goes nicely because it gets distributed. But once you inject hydrogen here, because this kind of a zone is not there, it will actually just go through like this. So then they need to actually design what should be the size of the nozzle so that as far as possible it can penetrate. So many of these aspects can be obtained through this modeling. How much time I have? I have exceeded? Okay, fine. So the other thing which we are doing, we actually have developed a simulation tool. Again, blast furnace is slowly it will get replaced because of blast furnace cannot operate without coke, carbon. So now we have what is known as a gas-based reduction process where gas is being put, hot gas, CO or hydrogen, etc. And then the iron ore in the form of balls, they put it at the top and they get reduced, and then in the bottom part they do cooling and they have to add some small amount of carbon for further processing. So these are now becoming more and more popular, and possibly if hydrogen become a reality, I don't know, whenever it is, renewable energy, because there are challenges you understand, because from renewable energy you produce electricity, that you split it and all those things. So it is more energy intensive, it is more cost. So still people are working on it. Anyway, so probably nuclear seems to be the middle solution. That's what I believe. So now in Government of India is also trying to have pilot plants where some of these things can be tested at the pilot scale. So we have developed a model which actually it's called HydriSim. So this we are trying to sell it to steel plants, etc. so that we actually customize to some of their furnaces, etc. So again, I will not go into the details, but I just tell you that actually there is a cooling gas which goes here, and there is a reducing gas which goes here. The flow has to be adjusted in such a way that if, for example, if you try to decrease the pressure too much, this gas will come down, or if it is too less, then it will not cool. So there is a balance of pressure and all those things. So many of those things can come out the simulation, and based on that they can actually design as well as find out what is the optimum flow, etc. So some of these things we have done it for example JSW, and these are, again, I will not go into the details, but I can just tell you that as plants are trying to put more and more hydrogen, so if you put more hydrogen, there are again the temperature of the gas which comes out, it decreases, and the product also gets affected. For example, just tell you how much metal, iron oxide has become metal. In the case of carbon monoxide, it is 95%, and if you replace it with hydrogen, then actually it really comes down. And also there is a region where actually the iron ore doesn't get used properly. So for example, Sweden, they are trying hybrid is a process where they are trying, and they are facing this problem. So the problem is because one should properly design the gas inlet and all those things. So you can try different height to diameter ratio. All those things can be studied using OpenFOAM, this kind of simulation tool, and then one can do studies which are the window of design or operation can really be brought down. So these are the two. I think I will not go into the next one because of the time, but I can just we have done it for other systems also, but let me just conclude my presentation by saying that for systems which are having multitude interconnected phenomena, which is what I was trying to and it is not just the conventional transport equation, you want to put your own physics, then OpenFOAM gives the flexibility to have one's own models. And the other thing is especially for industry, etc., it can be very easily customized, and of course it is also more cost effective because you don't have to pay every year annual fee. That is all. Thank you.
Thank you so much, Professor Vishwanathan. So any questions for him, because we have not we are actually running short of time, so we cannot take many questions, but a couple of questions.
Yeah. So we use the Ergens equation and also the particle size distribution, which is available. As it goes down, how it the changes, etc. Based on experiments, it's available. We don't predict the breakage and all those things. Of course, it's very much part of it.
But what model do you use to incorporate the porosity?
So it's basically porosity is not simulated. Porosity is assumed based on this one. But as far as gas flow is concerned, Ergens pressure, that term is very important. Rather, most of the time, even the inertial terms, we don't even have to solve the full Navier-Stokes equation, because those terms are also much smaller. Only delta P and the Ergens equation is sufficient, because you put all those things, again computation time increases and it is not going to give advantage. So again, that's the way we have done.
Thank you.
Okay, any more questions from anybody? Yeah, thanks a lot, sir. Professor Chandan, could you please come here and present him a small memento? Thank you so much, Professor Vishwanathan. So moving ahead with the talk sessions, I would request Professor Rochish to kindly present his talk. Professor Rochish Thaukar is from the Chemical Engineering Department of IIT Bombay. To know the audience, could you please let me know from which department you are? You can just raise your hands. People from chemical engineering? Okay, okay. And mechanical engineering? Okay. Lot of. And we also got registrations from art sciences. From art sciences, anybody? Okay. And MEMS, IIT Bombay? No one from. Okay. Aerospace department? Okay, okay. Okay. Nice to meet you all and welcome once again.
Okay, so good afternoon to all, and in a way I am an outlier here because what I present is not done on OpenFOAM. So I spoke to Payal and said if it is still appropriate for me to present here, and Chandan and Payal I think kindly agreed. So I think my motivation would be I will present to you some complex problems in electrohydrodynamics that we have looked at, and probably this will serve as motivation for you to try it out in OpenFOAM. And I will tell you the difficulties, the reason why we got into boundary element as a choice of our method. So I will talk about two problems, essentially electrosprays and what are called as electrocoalescers in refineries. These are huge units, 3 meter in diameter, maybe 20 meters in length, not as complex as blast furnaces, but they have this whole complexity of electric fields applied here. So essentially what you have are electrodes, and you put in the crude oil with around 10% of water as an emulsion and apply electric fields across these huge electrodes. And what happens at the heart of this process is coalescence of droplets under electric field. They grow larger and settle down. Okay. So that's the industrial process. In electrosprays, you take a liquid, these gaps typically are around 3 centimeter or so. You apply around 5 to 10 kilovolts of voltage. You have a collector plate and the liquid electrosprays. Okay. In the electrocoalescers, again the voltages are of the order of 16 to 20 kilovolts. We worked with Reliance Industries and they apply those order of voltages. But the fields here are much lower. They will be around 1 kilovolt per centimeter. Here you will get fields of the order of around 4 to 5 to 10 kilovolts per centimeter. So I'll look at what I'll present is a very microscopic process of what happens to a single droplet here, what happens to 2 droplets here, and the large scale modeling we typically do using methods like population balance method, and that's probably a challenge when we talk to industry. They want models, a CFD based model and all. There are few attempts in the literature, but not very satisfactory. So this is something you could try out, but I'll also what I want to communicate is the inherent complexity in the single droplet or 2 droplet process itself, which will make you appreciate the complexity of this process. So the work was done by Neha, Shubhankar and Sudeep. It's kind of work done around 3 to 4 years ago. So it's kind of, it's there in the literature through our paper. So let me just quickly introduce you to boundary integral method. It's an extremely powerful method, but with some restrictions. So it's valid only for operators such as Laplacian operator, Stokes law operator, biharmonic operators. If you want to use it for say Poisson equation, you will require special Green's functions. You will have Green's function with Hermite polynomials, or you might have Green's functions which have to be numerically calculated. So it gets a little involved there. But the biggest advantage is that for such operators you can use the Green divergence theorem, and then your domain reduces by 1. So if you are looking at a 3D domain, you only have to integrate over surfaces. That's a huge reduction in computational cost. If you have a 2D surface, then you just integrate over the boundaries. Okay, so that again is a huge computational saving. I am mostly going to present axisymmetric problems, and so in axisymmetric problems it essentially becomes a 1D problem where you integrate over the arc length of the droplet. So computationally we have been very efficient, but then it's very unforgiving. The results I present are through our own codes developed since around at least 2012 or so, and we didn't use the other common source of boundary element codes, which is Professor Pozrikidis's code in the open source, which quite a few people use. we started with that, ran into problems, and then at that point around 10-12 years ago we decided to have our own code. The key problem why it's a non-starter for a lot of academic groups is problems associated with handling singularities in the Green's functions. And when it works like a charm. The accuracies are unmatched. I will give you some numbers. But then if it is not coded properly, numerical instability is built in really fast and your whole simulation is destroyed. So I will get started with a problem. I'll be very brief on the physical problem and tell you the numerics, but the problem here is essentially how do charged droplets break. So if you put a charged droplet, you take a droplet, put some charge on it, it essentially breaks after a certain charge because the interfacial tension is not able to, the charge essentially overcomes the interfacial force. First given by Lord Rayleigh 1882, he did linear stability analysis, he found the critical charge. I will talk in terms of non-dimensional charge 8 pi for convenience. And then what you do is you take the drop, you put some perturbations, and then these perturbations grow and the droplet becomes unstable. Okay, that's the idea. Now, although the problem is fairly old, the linear stability analysis was done quite earlier. There were some analytical weakly nonlinear kind of analysis done. The first experimental demonstration came very late, around 2003 or so, by a group in Germany. And what they saw was you take the droplet, you levitate it. I have a whole presentation on this which I will not, but essentially for this talk what's important is that you take a charged droplet, it evaporates and builds a critical charge, and then it breaks in this manner, and it breaks non-linearly, as you can already see. A jet is released, all the excess charge is released, you go below the Rayleigh charge and then you regain the shape. That's really the process. And so we started off attempting to model this. So with respect to fluid mechanics, there are only two regimes that a boundary element method allows you. Stokes flow regime, where you throw out the inertial terms, or the potential flow regime, where you throw out the viscous term and have the potential flow approximation. These are the only two limits. That's one of the main reasons why it's not as popular. As soon as you have finite Reynolds number, you cannot apply Green divergence theorem. So that essentially is the bottleneck. But then if you have problems, for example biological problems, your low problems, it works like a charm. If you can make potential flow approximation in inviscid limit, it works like a charm. So we tried this in both the limits and we have physical reasons to justify that. But essentially what is happening here is this whole process happens in few microseconds. Okay. So this is how the whole idea of boundary integral method is. You essentially have a singular force at a certain domain, in a certain domain. You want to know the velocity at any point x naught because of a singular force at f. You have to identify, you have to construct a Green's function formulation. I will not get into details of it, but for Stokes flow, for example, they turn out to be the Stokeslet and the Stresslet. So these are kind of well documented in the literature. But then what happens is, if I want interfacial velocity, if I know the interfacial force, which could be your surface tension force, for example, I just integrate it over all the surface and I can get the interfacial velocity at this point. I can move this point with this interfacial velocity by kinematic condition, and you essentially have evolution of the droplet. You can put in electric stresses if your problem has electrostatics in it. So this is really the integral equation that you would want to solve. You put in the force discontinuity here, the Green's functions are specific to the problem, and then you could solve this. So maybe I can skip this, but the numerical implementation for an axisymmetric system will be have elements, solve all of those integral equations on the elements, and when these 2 points approach each other, the singular point and the observation point approach each other, there is a singularity. The singularity could be 1 by r or 1 by r cube depending on your functions. That has to be integrated very systematically. That is where most, I think, groups encounter problem. Unless you do it properly, you have numerical inaccuracies here, and then essentially you integrate this and solve. So I'll just quickly put up this. This is the problem which we eventually solved in this case. You have electrostatics solved through boundary element method. You have the fluid flow also solved through the boundary element method. And in this case, in this problem, when you put in the charge, the entire charge resides on the surface of the droplet. It's like an insoluble surfactant, for example. If you're solving problems of insoluble surfactant and the surfactant is lying only on the interface, as your droplet deforms, your surfactant concentration changes. And unless you do it accurately, you will have problems. The reason essentially being that the transport is related to the curvature of the interface. It's as simple as if your droplet expands, you will have reduction in the concentration. So when you write the surface concentration for a surfactant, there are always a curvature coupling terms. In our case, it couples with the charge density at the interface, and that is an accurate, this is extremely critical in these problems, that you conserve the total charge. So if I put a certain charge throughout the course of my simulation, if the charge is not conserved, you will get very non-physical results. So that we do using a finite volume method. So what we do is you do a boundary integral method plus a finite volume for the surfactant concentration on the interface. Okay. And so if you do that, then you can really solve such problems. We did that in the viscous limit. We also can do it in the potential flow limit. There is this nice model by Lundgren and Mancho, where you have integral equations for the stream function and the velocity potential, and then you can reconstruct the velocities, use the Bernoulli kind of equation and evolve the system. And of course for the charges you can have a similar formulation. So with this we got on with solving this problem, and what we saw was in the pictures also, if you see, just at the onset of breakup you see these two Taylor cones formed. Okay. So the way you do this problem is you start with a charge slightly less greater than the critical charge. So if your critical charge is 8 pi, you put 8 pi plus 0.1% of Rayleigh charge, that is the accuracy we have, and then it starts breaking if you put a spheroidal deformation. Okay. And then it forms a Taylor cone. Now if you look at instantaneous charge relaxation, you actually, your code stops at this point. You have Taylor cone singularities and your code stops. But in experiments you see this. So we implemented a finite conductivity model, which I just mentioned, and then we could actually predict the whole thing. So I will just maybe quickly play the two videos. When we don't implement, we implement instantaneous charge relaxation. Oops, sorry. So if we implement instantaneous charge relaxation, you will see it will form Taylor cones and stop. But if you put in charge relaxation, then you can actually get these jets, and then you will have two progeny droplets at the two ends. Okay. And now what do you do this in a boundary element method? Now it's not a method like level set or phase field, where you have some function which automatically cuts these droplets. That's always an issue in the boundary element method. Okay. So we kind of handled this. I'll maybe talk about this again, but we could do such simulations where we had a charge drop oscillating in some potential, and then these are our experiments, and we could nicely simulate the simultaneous. So this is a problem where you have simultaneous translation and deformation coupling, and in fact the breakup happens because of this coupling. This is what we showed in the paper that's out there. It was very critical that you couple the translation and deformation correctly and simultaneously, and that led to our first demonstration of what is called as a transcritical instability in charge drops. It was there in the literature in terms of analytical results. We gave the first experimental and numerical demonstration of this in an actual system, and the point of relevance probably for this talk is, you know, unless you have the accuracy that we had, say for example if it's 8 pi, if I put just 1% less, I get a, so if you want to construct this bifurcation diagram accurately, you have to have your conservation of charge and volume accurately, and in these simulations our charge is conserved to less than 1% loss, our mass is conserved to less than 1%, and any inaccurate modeling leads to breakdown of your simulation, that I can guarantee. We've been lately trying to do this in COMSOL multiphysics and facing enormous problem. This is kind of a 4 or 5 year old simulations that we did. I thought things would have improved. Now we still have a lot of challenges, especially in instability problems. I get a lot of spurious, I mean, like, of course you'll always question whether it's correctly implemented, but I still feel that there are numerical challenges here if you want to put it in OpenFOAM. There is, we kind of were the first to suggest that the Rayleigh breakup is conductivity dependent. If you do breakup of a droplet with less conductivity or more conductivity, you get qualitatively different modes of breakup, which was not reported in the literature. We first saw this in experiments. This is a low conductivity thing where you eject one droplet at a time. In the high conductivity thing, you have the detaching, and we could capture it nicely in our simulations. And I will tell you what was special about this in the boundary element context. So you will see that a jet is formed. In this case, you will have a detachment. You will have here one drop ejecting at a time, like this. Okay. So this ejects, and then now in boundary integral method, you have to do this discontinuously. When your code stops at the singular point, you have to stop the code, and you have we did at least a manual intervention. The first problem we encountered was, when do we stop the code? When the necking happens. So when the necking happens, you want your element, the boundary element, to be much smaller than the neck diameter, because that essentially is at the heart of the accuracy. So what we realized was an exponential breakup. When you calculate the neck radius as a function of time, there is an exponential shrinkage of the neck. At some point we take a call that we would cut it, and then we detach the progeny droplet, we reconstitute the interface, and then we continue the next breakup and so on. So this was one which at least to the best of our knowledge wasn't reported in the literature. The second problem is the refinery problem, as I mentioned, on electrocoalescence. These are two droplets. As I said, at the heart of the process is interaction of two droplets. You will see in this video that the two droplets come together and coalesce. This is at low electric fields, so they have coalesced, whereas at high electric fields you see that the droplets don't coalesce, but they come together, they touch, and then they kind of detach. The physics of this was given by Professor Stone's group, where they essentially say that there is a liquid bridge which is always formed at before coalescence, and the pressure in the liquid bridge essentially decides whether it's a coalescence or non-coalescence, and so it's decided by this cone angle beta, and it's essentially a play of two curvatures, the azimuthal curvature and the meridional curvature. So if your meridional curvature is large, as it is in the case of electric field, your positive pressure, your negative pressure is less, so the azimuthal curvature generates positive pressure, pushes the liquid out, you have non-coalescence. Now in boundary integral formalism, what we did was we simulate two droplets, bring them together, make a contact, then the code stops, okay, and so then we connect, we get the cone angle, we connect a bridge artificially by hand by solving Euler-Lagrange equations for the bridge. We place the bridge here, and then we coalescence, or you have non-coalescence, and we could map it to this cone angle that is formed in the case of coalescing droplets or in the case of non-coalescing droplets. So this again was first of its kind intervention in BEM, where we could stop, reconstitute, and then redo the simulation. So I think I'll mostly stop with this. We've incorporated elasticity, we've simulated red blood cells using boundary integral method. We had the Scalak model. It had huge issues with stiffness, because you have to conserve the membrane area. We have, if you include bending in these problems, which is fourth derivative of position, Laplace derivative of curvature, the numerical inaccuracies are too much, so you have to handle it carefully, and all of this. So I don't know if it's still good to write your own code. There are open sources available, one could try that out, but I think it remains a challenge, at least the problems in electrohydrodynamics, to put it in a formalism like OpenFOAM, and we have, I feel, very accurate simulations which one could use to test it out for their accuracy, and the relevance I think is pretty large in soft matter, chemical engineering. So it's certainly not a problem of these problems being industrially relevant. So I think I'll stop with this.
Thank you so much, Professor Ruchish. Maybe we can take only one question, because we are really running short of time.
Just curious about why this thing
because electric field is in single direction.
Yeah.
Is it because the charges
In the Rayleigh or the first or second?
the Taylor cone formation, the stretching which you showed?
Yeah, yeah, yeah.
So
yeah.
why this? Because we need a tension on both ends.
Yeah.
to
So
achieve
no,
this.
no, no. So as you form, you first give a small spheroidal perturbation. So you give a perturbation like this. So wherever is the region of high curvature, the charges move there, and then it's kind of a self-reinforcing instability.
Okay, so the plus and minus go in the opposite ends.
Opposite direction.
And electric field is in the same direction.
Yeah.
So that's why.
Yeah.
Okay, thank you.
We could construct the entire mechanism. We've reported this.
Okay, thank you so much, Professor Rajesh. So I would request Professor Chandan to kindly present him a memento. Thank you, sir. To move ahead, we have Professor Abhishek Ranjan with us from the Mechanical Engineering Department of IIT Bombay. Yes, we are actually moving very late. What we'll do is we will push the post-lunch sessions with 15 minutes.
Hi everyone. Am I audible at the back? Back? Yeah. So first of all, thanks to Ms. Payal for inviting me to give this talk. I'll be talking about modeling and understanding of current-driven flows, current-driven MHD flows using OpenFOAM, work which I've been doing with my students Swapnil, Ravi. Swapnil is now a postdoc in the TCS project, and some other names of the students and collaborators. So why should we study these kind of flows? They are important in several industrial applications. One of the important applications that I have been working on is something called liquid metal battery. You may have heard about the application of or the need of energy storage at grid scale that is required to have widespread solar and wind energy, to be used for charging electric vehicles, for instance. So what happens in the liquid metal battery is that you have three elements like a typical battery, but they are in liquid state, or at least two of them are in liquid state, and in the discharge cycle, the ion from the metal A, which is a typically electronegative metal, it goes traverses through the electrolyte, goes to the positive electrode and forms an alloy with the metal B, and the opposite happens in the charge cycle. So in the discharge cycle you get electron moving in the outer circuit, which you can use to charge or to use for your useful purpose, and then you have to put electricity inside to charge the battery. So clearly you can see that this is a problem where there is a current involved, so there could be current driven flows, and there are interfaces, there could be liquid interfaces, there are of course thermal effects, solitary effects, so there is a complex multiphysics coupling between different phenomena which can happen in this system. Some more examples of current driven flows can happen in vacuum arc remelting and DC arc furnace. Once again, in this case the current, of course the currents are very huge in these examples. In arc remelting you want to have the current in order of kiloamperes sometimes to be used to melt the metal, and then here apart from current driven flows you also have buoyancy and surface tension effects which you also have in the liquid metal battery, and something similar is in the case of DC arc furnace, where the idea is to be able to use current to melt the liquid metal, and again the interaction of current driven flows with buoyancy becomes important in this application as well. Another very futuristic application is something called MPD thruster. So for space applications, deep space applications where you cannot use chemical fuels anymore, you have to use something else, and people have proposed that perhaps with the help of nuclear fusion or nuclear fuel and by able to accelerate some plasma, it is possible to have at least some thrust even in outer space. So that is an idea which is still under development, but people have developed some similar other thrusters, like for example Hall thrusters are already under development and they are already deployed. Yeah, so there are different multiphysics phenomena in liquid metal batteries. My focus so far has been mainly on modeling the MHD effects. So MHD, within MHD there are several kinds of phenomena which can occur. I would like to focus on current driven flows for this talk, but there are flows which can occur because of external magnetic field. There are flows which can occur because of interfaces and interface coupling, and also because of the variation of magnetic field in the domain. I will focus on electrovortex flows. I will talk about what that is in a bit, but in any practical application, as you would appreciate, this will occur in coupling or in the presence of other effects. For example, thermal effects, chemical effects, Joule effects. Joule heating can also be important. In fact, to keep a battery in liquid state, if it has metals, one would like to have some heating present, so it is sort of desirable also. What happens in some real commercial batteries is that the ions which come and try to enter the positive electrode, instead of getting well mixed, what happens is, because they are lighter than the bottom electrode, there is some stratification which happens at that top part, and that hinders more ions from entering the positive electrode, and that ends up affecting the voltage efficiency. That is not good for battery. A battery has to be efficient, reasonably safe, of course long life. These are all requirements from a good battery. So it is of interest to people in chemical engineering, mechanical engineering, also battery designers, to be able to mix these ions little bit in the positive electrode. Now that is where the MHD effects or current driven MHD effects can or cannot be useful. That is still under investigation. People have been trying to use some of these to explore whether they can be used to increase the voltage efficiency of a battery or not. And there are of course other phenomena which I will not be talking about, and they can also be interesting and important in the context of liquid metal battery. Yeah, so just a very quick recap, because not all of us are very we have studied of course high school physics, but some of the things we may have forgotten. So a very quick recap: in a conducting fluid, if you have a very large current, that current has its own magnetic field, and in the case where the Lorentz force, which is J cross B, when it is non-conservative, it is not balanced by pressure gradient. So suppose there is a current pass, current is applied to a quiescent conducting fluid, the non-conservative nature of the force can lead to flow being initiated. Okay, once the flow arises, that flow will have an induced EMF which will add to the current. So current will become J equal to J naught plus small j, which will be time dependent, as you can guess. That small current will have its own magnetic field. So it may so happen that sometimes these can be ignored, but by and large one has to be careful depending on the circumstances and the parameters, that we have to be able to include all of these effects in our simulations. Suppose we are building a solver, that is very crucial. Yeah, so suppose J is small, we can ignore suppose these induced effects are very small, we can ignore these and put Lorentz force as J naught cross B naught, but if not, we have to consider the entire 4 terms. So as you can see, they are all vectors, and J cross B is going to be alone comprising of 4 terms, all of which are vectors in 3 dimensions. So little bit about basic governing equations. Now we know that electromagnetics, we have to worry about Maxwell's equations. What people do in the community is that they combine these and write a single equation which is called induction equation, and that is typically solved along with Navier-Stokes. That is a general approach which is applicable in many contexts, even for astrophysics, geophysics applications. Now this is a coupling that I was talking about a bit earlier. So we use, let us say if we have magnetic field, if we know what is the flow, we can use Ohm's law, find the Lorentz force with the help of Maxwell's equations, feed that back into momentum equation, and this coupling is you can say two-way coupling. Now what happens in liquid metals is that one can have something called low RM MHD approximation, where it's possible to ignore some of the terms here in this equation. So we can ignore the entire left hand side and also this term. So the term which is important is only this one, diffusion, which makes this much easier to solve and make progress on. So what happens is, if the low RM approximation is applicable, which is true when this parameter is small compared to 1, in that case we do not have to worry about this equation completely, we have to worry about only Poisson's equation for electric potential, and sometimes what happens is even this term is very small. So then it becomes completely decoupled, it becomes 1D, you can say it becomes one-way coupling, where all you need is a source term, the Lorentz force in the momentum equation, and that is it. That will be a constant term in the equation, and you can simulate phenomena with a fixed source, fixed Lorentz force. That is very rarely the case. Typically what happens is you have something like a coupling without the magnetic field changing, where you have some current which will change depending on U cross B, and that will require to be fed again to Lorentz force, which will change the velocity. So this coupling is typically present in many applications. Yeah, so this, after the coupling is gone, what we have is this set of equations to worry about. Yeah, so typically this current driven flows, they arise because of the non-conservative nature of Lorentz force, which is shown schematically here by the help of a point current. Now in this case what is happening is that the Lorentz force is non-conservative, and that will initiate flow, and this is what is seen in this simulations here, and this simulation is just for a single part of the liquid metal battery, a single element, not the complete battery. So here what is seen here is the toroidal vortex. So there is a jet in the center, it comes and hits the boundary here and curls around, and this is 3D, in 3D it looks like a torus. Now typically these flows are characterized by something called S parameter, EVF parameter, which is a ratio of Lorentz force to viscous force. Now as you can see, there is no dimension or no indication of the geometry aspect of the current lines. It is purely ratio of Lorentz force, which is I square here, because there is J, there is a B, becomes I square, and everything else is properties. So we were very curious that a flow which seems to be arising only because of the nature of current lines, majority because of current lines, and of course the current value is also important. How is it that the main non-dimensional parameter lacks that effect inside it? So that was one of the motivating factors which we tried to attack, and I will have some answers to share about that very shortly. Very quickly I will go through the equation that we solved in OpenFOAM. OpenFOAM already has Navier-Stokes, so we have to add a source term for the Lorentz force, and I said that in the limit of one-way coupling we can only worry about a simple Laplace equation, and we can find current density from Laplace equation. What we do need is something called Biot-Savart law, because we have a current, and you know from high school physics that the current anywhere will affect the magnetic field at any point. So it becomes a integral equation which has to be taken care of. Thankfully OpenFOAM being open source code, we were able to add that. This is a volumetric case of that. This is what we used to get mu naught I by 2 pi r. If you remember, current because of a current carrying wire, magnetic field is mu naught I by 2 pi r. That is what is required to get that. So this thing was coded by one of my students, and after that we could put J cross B in the momentum equation and go ahead with the simulations. So let us see what we get. These are some boundary conditions. We have current entering from a single region here and exiting the entire bigger region. That is important for the current to be able to diverge. Remember that is the important ingredient in creating electrovortex flow in the first place. Some good independence. Yeah, so this is a movie which shows how the flow develops. I will not talk about the left hand side, that is about something called vorticity and its different contours. So you can see that jet gets created because of the Lorentz force distribution in this corner, and then it goes down, curls, develops, and at some point it may become steady. That depends on the how large or how small the current is. Okay, so now I am going to show you some pictures where what happens if I change this diameter, the diameter of the current collector, the region from where the current enters. So in all cases the flow pitches are somewhat similar, but not completely similar. In all cases we have some central jet, a torus is formed, but the jet becomes wider, and we see in the velocity magnitude that the velocity magnitude drops from the smallest current character to the biggest current character. That is this is the weakest electrovortice flow, this is the strongest electrovortice flow. Okay, so that means the question is, should this be incorporated in the non-dimensional number? We thought that should be. So for that CFD of course is useful because one can do a variety of simulations in 3D, and we also did some theoretical calculations by doing a balance of vorticity, advection and production by in the Lorentz force, and that led us to a theoretical estimate from which we could get a modified, you can say a modified non-dimensional number, which we think is a better parameter to talk about electrovortice flow completely. So I will not have time to discuss about this in more detail, but if you give me another opportunity maybe I can. So yeah, so this is the final result in the sense that the literature says we should use S, which has only current and properties, but we say if we also include K, at least for cylindrical case, if we also include K, we are more completely able to describe the electrovortice flows in cylindrical domains. Yeah, so this also has to do with the scaling of Reynolds number to the so basically inertia to Lorentz balance is what is required to get this. So we are saying now that rather than having Re as proportional to under root of S, we should have Re as under root of Sm. So it's like a new non-dimensional number proposed to be able to characterize these for cylindrical domains. Yeah, so the work in progress is that in real cases we have this is similar to what Professor Shiva showed. In fact, there was a strong water jet coming and hitting a steel pool. So here I have a metal region and an electrolyte region, they have massively different conductivities. This is order 10 or order 100, this is order 10 to the power 6, which means there is an interface here which across which there is going to be a very large change of conductivity. In this case we cannot ignore this term, we have to take it into account, and we also have to take into account the change of conductivity from top to bottom. And if the interface starts to move, this is of course a simulation with the help of VOF, if the interface starts to move, we also expect that the current lines which were almost vertical, they will also start to dance around, because the current is depending on the nature of interface. So this is the first time that anybody has simulated this effect of the moving interface on the current lines, but I am still not very sure about some spurious large currents at the interface. So we are still investigating whether it's fully accurate or not, because it's very easy to make mistakes in numerics if you have such stiff problems. So another work in progress is what happens if I integrate or include stratification effects along with electrovortice flow. So this is a work funded by TCS, and here we see that if I have a lot of stratification because of the solutile effects, the electrovortice flow is completely overwhelmed, is completely killed. So looking at electrovortice flow alone is insufficient. It's a very important information for people who are going to design batteries, because as you can see slowly and slowly stratification becomes very, very strong, and the effect of the flow is diminishing more and more. This will obviously have an effect on the efficiency of the cell, because this means that there is not going to be much mixing happening in the entire domain, and efficiency will probably become very less. Yeah, so finally some summary. It's possible to use OpenFOAM for doing almost anything except for maybe problems which involve maybe too many solids and liquids and their coupling. That becomes a bit challenging. Even for that, people have proposed something called parent-child mesh technique. So what happens here is that in parent mesh you solve the entire you can say potential equation, Laplace equation, and then you take that information and solve for flow only in some child meshes and couple them together, a bit like conjugate heat transfer, but somewhat more complicated. So we have also been trying this lately with the MTech student, and yeah, and if you have any questions, I will be very, very happy to answer. Yeah, thank you.
Thank you so much, sir. Any questions for Professor Ranjan?
Told that with the non-dimensional number, which
Yeah.
basically decides the current, the vorticity magnitude increases, but have you seen the mixing or the vortex convection? Are they correlated with that?
Yeah, So, there are two different things, one is the parameter which is completely it is obtained by doing only current driven flows with no stratification or no buoyancy effects. So, that is this is a classical case, you can say it is like a canonical like pipe flow. In a real life pipe flow may occur with heat transfer and mass transfer. So, it is when we go to electrovortex flow plus something else which is stratification, then we start to see that the electrovortex flow is totally overwhelmed by stratification effects. Now, in that case, even in that case the modified parameter is useful, because suppose someone wants to increase mixing, the parameter says that you make the area of the current collector smaller and smaller. So, that has been observed to make the jet stronger,
Right.
but eventually even in that case stratification will overwhelm it, because we can see that these are, if I go back, yeah, I think it's stuck.
That's fine. I was
Yeah.
just curious that in case of two-way coupling, I mean,
Yes.
whether the vortex convection and the electrical lines that you showed, are they correlated in terms of their dynamics or not?
Yes. So, what we see as the vortex is arises because of electromagnetic force. So, it is a cause and effect. Electromagnetic force is the driving force, and of course, there
But
is
that's
some
for
resistance.
one-way coupling, but for two-way coupling, they both will affect each other, right?
So, for two-way coupling we have to of course include other terms which we have ignored, and for liquid metals we do not have to worry about two-way coupling, because for that there is something called magnetic Reynolds number, that is almost always less than 1.
I see.
But suppose if I go to a different problem, for example Earth's core, there we cannot ignore the magnetic field. So, magnetic field changes and that will affect the flow and it will affect the current. So, there one has to consider, I mean it becomes more complex to analyze.
Sure. We can talk later.
Yeah.
For the sake of time, thank you.
Yeah, thank you.
Yeah. Could you please come here and present the memento? Sorry, every time we'll yeah. Other professors.
Okay, let's go ahead, and I think I wanted to take the opportunity to call Professor Amit Agrawal for the next talk, because he was also my PhD examiner. So, so I think I'm looking forward to listening to your ongoing work. Thanks.
So, good afternoon everyone. So, I will be talking about sorry, याद हो रहा है यहाँ पर, अच्छा ऑनलाइन भी है. अभी आया, यहाँ नहीं आ रहा लेकिन. Okay, so ready? Okay. Yeah, so good afternoon. I will be talking about numerical modeling of blood flow in microchannels. So this is something which is done, I mean, I really don't know OpenFOAM, but this work has been done by my PhD student, Shivji Prasad Yadav. And of course, all the numerical details are handled by Atul, my colleague. So the problem is, if you look at blood, yeah, screen pe nahi aa raha. यहाँ पर कनेक्शन प्रॉब्लम है क्या? Okay. Okay, so if you look at the basic problem is that if you take blood, it's a suspension of lot of cells in liquid, which is plasma, and the plasma has where the most of the information about the human body is. So once we go for a blood test, I mean, blood test is one of the most commonly sort of prescribed things to do if a patient is not well. Oops. किस तो प्रॉब्लम है यहाँ पर? So we would like to do the same thing on a micro device, and if you have to do that, then you have to construct a micro device which can do this sort of a thing at the micro scale. So the separation of plasma and the remaining part should happen, and you can look at the composition of the cells of blood, which is a lot of blood cells, some WBCs, and the remaining is your plasma. And of course, there are a lot of other cells which we are not getting into. So these are some details about what is happening, I mean, in terms of numbers of for the sizes of RBCs, WBCs, platelets is what you have. And as I said, conventionally, the centrifuge is what is used, which is a huge setup, requires trained manpower, and it's a time-consuming process. So what we had done in the past is to develop a microfluidic placed or a platform which can do this separation for you. So you can have active or passive ways of separation, and passive is what we have used. So there are again a lot of details in here about passive. So I will sort of, this is just to motivate the problem, but we can move ahead and say that there are a lot of interesting effects or interesting biophysical phenomena that is available when you start getting to these things. And because we are interested in the modeling, we'll have to sort of think about or understand these things very carefully. So you can look at margination of the cells away from the walls, which leads to a cell-free region. There is something which is the Farias effect and the Farias-Lipist effect, which are also coming to the picture. So all these things have to be somehow brought in. And some of these things are shown pictorially here. So the cells, you can see, have a tendency, if the size is smaller than a certain size, I mean the capillary size is smaller than a certain size, then the cells have a tendency to move away from the walls, and we have a cell-free region, for example. And again, there is this other effect which is also shown through a picture where you have cells coming in at the junction, and then depending on the flow rate, which is higher, the higher. So all the cells tend to flow in the branch which has the higher flow rate. So this is also known as the bifurcation law, and there are certain conditions under which this works. These are sort of the things that we would like to bring in, both the biophysical effects and the geometric effects like what we are showing here. So if you want to sort of solve these problems, then it becomes a reasonably complicated problem. So let me just move ahead and say that so what we have done in the past is to develop a few blood-based separation devices, a blood plasma separation device, a platelet-rich separation device, a WBC enrichment device. So these are various devices that have been developed in our lab. And all these times we have used blood, done a lot of experiments, and that is how these devices could be developed. So what we were looking for, which is the motivation for this work, is to have a numerical framework under which something similar to whatever physical experiments can give us. Numerically, we should be able to do that, and of course, that has its own advantages in terms of not using any blood, or not, or at least minimizing the number of blood-based experiments that one has to do, and also being able to do a lot more parametrics than what is physically possible in these, or like possible in these physical experiments. So the idea was that should help us reduce the cycle time for developing these sort of devices. So that was the actual objective, and this was essentially done in 3 parts. We wanted to first develop a numerical framework, and then test the accuracy of this numerical framework, and of course use that further as an optimization tool, and sort of look at what sort of a performance we get. Now, we will now get into the numerical part. So there are quite a few options that one has as to how exactly one would go about modeling this. One can have some sort of a microscopic approach, which is primarily, let us say, done through molecular dynamics, which has lot of ability to bring in lot of interesting insights. I mean, but now you are essentially looking at the length scales. You can see that we are actually looking at very small length scales, trying to solve for that. But it leads to the range of length scales that you can actually solve in your problem is much smaller. The time scales becomes much large. So there is a huge computational cost which is involved in there, and you may not be able to solve an engineering problem. So the other approach is, of course, some sort of a mesoscopic approach, which is essentially works in this sort of a range, where you are trying to sort of model blood inside the microchannels, having length scales of the order of a few RBCs. So earlier we were looking at much smaller time scales, but here the length scales are of the order of a few RBCs. And we are still working with low hematocrit, means that number of actual cells that are being simulated is small. And this is, again, involves a lot of computational cost. Typically, it is implemented for 2D geometry, and using one of the methods which has been given here with the references given here. And it still involves a lot of computational cost. So this is also sort of out, and therefore we want to look at some sort of a macroscopic approach, where we can bring in one of these. So we essentially try to solve the Navier-Stokes model, the equations with certain models in there, which could be either a single phase model or a 2-phase model. And this is what we are going to talk about, and we will see what sort of an accuracy, etc., we can get through this approach. So if we look at the details, so this is, we are solving the continuity equation, the momentum equation. So this is the single phase model that I'm looking at first. And then we are solving for the hematocrit. And then there are certain terms, as we can see. There is this spatially varying interaction frequency term. There is something which is taking care of the viscosity being varying in space. That is also being modeled. And then there is this Brownian diffusion, which is getting modeled through this third term here, or at least. So, and then again, there are certain details about the viscosity being a function of the concentration itself. So that's how the coupling between the two equations are. And again, this can be solved through one of these models, the Apostolis and Beres model, or ABVM as we are calling it, or the other models, which is this Krieger viscosity model, which is where viscosity is dependent on the concentration of the local concentration of the hematocrit. And you can see that, so that was this, these are the standard models, but we also realize that these models are not good enough, so there are certain modifications that have to be required. So we essentially introduced another term, which is here, which is this AS term. So this term was later on sort of introduced by us in order to improve the accuracy of these models. And so this is how these expressions were obtained for this AS. And once we bring these models into the picture, we see that we do get, so we started now solving a few problems. So this is a simple flow in a tube, a small tube. So the geometry has been given here. And you can see that if you don't bring in this additional modification, and if you do that, so then you will have these 3 possibilities. with AS, I mean this parameter here being constant, or it is being varying with the hematocrit as given here. And so these are the various options that we have, and we see that once we start, I mean the model that we have proposed seems to have a much better accuracy in terms of, I mean there are still certain spurious things that you get, but there is still an improvement in terms of the accuracy of the model, especially close to the center line of the tube that we have. And it's much better than whatever people had earlier. And then we can also look at or sort of extend this to start looking at the, if we change the dimensions of this tube, then what happens. So again, there are a lot of details here. I will not necessarily get into the details. I will just try to sort of walk you through how these things, simulations could be done. And you can see that the present model predicts the hematocrit profile reasonably well. Okay, near the wall, as we said, that there are still issues, but otherwise this model seems to work pretty well. Okay, and then we also wanted to look at another geometry, which was a rectangular cross section. So the geometry is shown here, and then you can see that these are now compared against a lot of other some experimental data and other simulation models, and you can see that things seems to be reasonably well is what the bottom line here is. So again, one can get into the details. Some of these details are given in our papers. We can look at, so where these things, these results are discussed in more detail. So I will skip all those details and move ahead and say that, okay, we can, so this model again is again compared. So basically again, the numerical framework, the advantages that we have, once we have a sort of a reasonably good model, one can do detailed parametrics with that, changing the aspect ratio or the hematocrit loading, and see how well these models are behaving. So again, there are very detailed observations which are given here. In the interest of time, I will not get into all of that. But so it's again, so we sort of document as to how things vary if you vary these aspect ratios and the hematocrit loading. And these figures give you the idea of how, if you look at the cross section, how exactly the cells are moving and where the concentration is changing. And you can make again certain observations with respect to that RBCs are more prominent, or they migrate more in the span-wise direction as compared to the lateral direction. So this is one of the important observations that one can make from all these detailed velocity profiles, like what you see here, or the concentration profiles that like what you see here. I mean, so you can again do a detailed detailed simulations, and you can get these results. So the idea is that we can start off with a simple, so what we have introduced a single phase model, which is good for simple geometries and for a low Reynolds number. And but if you want to really separate out, if you want to look at the problem that I was talking about, you start with blood, you want to separate out the cells, and you want to separate out the plasma, then this model is not good enough. And we'll have to go with some sort of a two-phase model, which was attempted next. So here what is happening is that we have two separate equations for plasma and for the cells which are there, and then you try to again write out all these stress terms. Okay, again, so there is good amount of modeling which is involved for each of these. And so you can, so again, each of these terms are, there are again, as I said, there are a lot of details which are available, which gives you how exactly these stresses have to be calculated. Now, so I mean, in some sense, the novelty of this was to put all these things together. I mean, in terms of, I mean, a lot of these are like known models, but people have not been able to put it together and actually simulate blood flow in microchannels. Okay, so this is where, so once we did this work, I mean, a single phase work itself generated a lot of interest from the community, and this two-phase work has been further, I mean, has also been well received. And I will show that with using this model, you can actually go to very complex geometries, and you can actually get results which are very close to what experiments would do. So we will now start looking at a few cases. Again, we go back to a uniform rectangular cross-section microchannel and show that you can see that there's a lot of comparison with experimental data. You get very good comparison, comparison with what experiments give you. And of course, there is more to it than, I mean, you can not just plot the I mean these sort of profiles which for which experimental data is available, but lot of other parameters as well. Okay, so again the basic point is that the comparison is good with experiments, and if you look at the average velocity, this is something which is dependent on the hematocrit, and you can see a value varying from 1.82 to 1.5 depending on what is the type of hematocrits that you have. So again, so let me skip this in the interest of time, this slide, and go to another geometry which is slightly more complicated. So we are starting off with the simple geometry and going to a more complicated geometry which has the sudden change in the cross section. So it's a suddenly expanded microchannel, and this is the experiments. All these are the experimental images that are available, and these are our simulations for the same set of conditions. And you can see that there is a very good one-to-one correlation between the two of them. Okay, and there is again some, wherever we could do a one-to-one comparison, we did that. Otherwise, we compared the images from whatever is available in the literature or from our lab to whatever we are, I mean, the simulations are giving us. So again, so this is another case which we have a certain expansion, contraction first, and then there's an expansion. Again, as something which is of lot of interest to us, because when you are working with these micro devices, you are essentially looking at geometries like these. So again, the simulations have been done. Okay, and I will move on, and I will look at another case where we have a bifurcation, like a Y-shaped bifurcation which is happening, and then you have again things coming together. So in this case, you can see that at the first bifurcation and the second bifurcation or joining, where the streamlines will rejoin, there is a lot of interest that you would have, and this is where you can see that there is experimental data which is available, which is very noisy, okay, and you can actually pick up all these signals very well from the simulation. So you can actually show that how exactly these two dips, which are essentially corresponding to two branches, will come together or disappear. So you can see that this peak would be very clearly sort of shown through these simulations. And there is a lot of interesting physics that one can study based on these numerical data. Okay, so this is how, if you just plot the hematocrit, this is the type of results that you would get. And again, you can have one more case, which is like in a network of microchannels, where again we saw that there is some experimental data which was available. So this is the type of experimental data that we have, and we wanted to sort of see whether we are able to reproduce that in our case or not. And the overall conclusion is that yes, I mean, it can be very nicely done, is what the bottom line here is. And in all these cases, we have been looking at quantifying what is the cell-free layer that we get in our cases, and that is a parameter that is typically reported in the experiment. So you can do a one-to-one comparison between the two of them. Otherwise, you can compare the concentration by the colors and see how the colors in the two cases are changing, which is an indication of the movement of the RBCs within the channel. Okay, so now we will move ahead, and other geometries, more complicated geometry where there is a bifurcation. So in this case, this is a picture which is taken from our own lab, and this is the picture this is what we get from our simulations. So this is a different type of percentage of hematocrit, 7%, and this is like 24%. So this is the number of RBCs as you keep on increasing that in blood. How do the results change? And when you go to 45%, so you can see that this is what we measured in the lab, and this is what we see in the simulations, both of them being in-house done. And there is a reasonably good correlation between them. One can find out what is the type of separation efficiency one gets, okay, and one can then track or compare the separation efficiency that one has from the experiments versus what the simulations would give us, which is actually turning out to be pretty good. Not just for this case, but then we start going in for more complex geometries like this tau-shaped geometry, where there is curvature which is also involved. So there is a centrifugal force that you are also bringing in, and of course there is change in cross-sectional area. There is a bifurcation. So there are enough complicated features that are actually being simulated, and you can see that again there is a one-to-one comparison on the separation efficiency that we get from the experiments and the simulations, and we see that it is not too bad. Okay, so I think this is pretty much what we have. One can actually go on and compare a lot of other geometries, so, but I think we will just sort of try to wrap up and say that once we have such a tool, then you can actually vary a lot of other parameters. That's what we started off by saying, that if you want to vary the depth or the bending ratio and bending radius and so on, then you can actually see how these parameters are expected to sort of behave. For example, one can do, for example, if you have two bifurcations or two such junctions, then how or the two construction zones which are available. So then you can also see, we can first simulate and then go in for physical experiment. So that's the sort of the conclusion that I would like to draw. And so in summary, we essentially went it from a single phase to a two-phase model. And two-phase model is actually good for studying very complex sort of a network of channels. And if you were to look at a direct comparison of what a single phase can do and what a two-phase model can do, a single phase model is sort of good for a simple geometry with certain dimensions, certain constraints in there, whereas here we could see that we can do a simple as well as complex geometries with 20 micron greater than dimensions, dimensions greater than 20 microns. This is good for hematocrit range of less than, in the range of 0 to 50%. This is, I mean, physiologically we have like 45% is what in our blood. So if we can actually simulate all of that, it's actually very good. But here the constraint is on Reynolds number that is typically that you can simulate with, whereas here you can go to a much larger Reynolds numbers, and while covering the entire range of hematocrit. And so this model is good for understanding blood dynamics in simple geometry. And we showed you a lot of results about the accuracy of this without getting to the details, whereas here you will see in the two-phase model, you can see that you can actually simulate the movement of blood, plasma, and RBCs in more complex geometries. And you can also use as an optimization tool for studying blood plasma separation and other devices. So I mean, okay, so if as an extension, now if somebody is interested, there are a lot of possibilities. One can do, for example, start accounting for the sizes, the other elements which are there. Lift and drag forces can be more carefully taken into account. So there could be anisotropic parameters which are associated with the local hematocrit, and so all these things can be. There is a possibility to bring in all these effects more realistically and simulate things. So this is the last slide, which sort of gives there are so many other elements in there in blood, and we have primarily focused on RBCs. One can also try to bring in additional things like platelets into the picture and see how exactly things are varying. So as we said in the beginning, we have developed not just a blood plasma separated device, which is essentially around these two elements, but we also have devices which can do other things. But we are not able to simulate them yet, but hopefully we can, we can extend them and simulate these other cases as well here. So with this, let me just stop and say that all this work was done by Shivji Prasad Yadav, former PhD student, and these are the people who have contributed from the experimental side for the blood plasma separated device as well as for the platelet-rich plasma separated device. So thanks to all of them. Yeah. So these are all 3D simulations. These 2D, yeah, we did 2D at one point of time, but because all our separate devices, we wanted to compare it with the real devices. We wanted to compare it. So actual one-on-one comparison, that's where we wanted to do, or we went in only for 3D simulations here. Sorry. No, there are two phases, etc., which are there, right? Yeah. You showed different topologies of the microscale. So how you determine that, okay, I'm done with this one, which one should Yeah, so that's a separate, very detailed experimental these things which were done earlier in the past. So based on that, so there is a very like a natural progression or a slow progression from one geometry to the other geometry, logical progression I should say, which has happened. So this is like a work which has taken us a decade or more. So it's a very detailed work, very lot of students, as you can see, have worked on it. So that's where we sort of understand how to sort of do it. Here the focus was just to look at whether we can actually simulate them, all these complex geometries, and get realistic results, which is what we seem to have. And I just tried to show you the two models through which this evolution, this numerical evolution has happened, not the design evolution. So we are, I mean, depending on what exactly, how you want to optimize, from what point of view you want to optimize. But the thing is that we now have a tool which will give you very realistic, so what you would expect in experiments is what you would, this tool is capable of. And now from what point of view you are doing it, that is something that you still have to. So medical point of view, they are interested in separating out a particular species. Okay, so they may be interested in just selectively removing the platelets or WBCs, or some, let us say there are cancerous cells which are there, they want to trap that. So that is their sort of objective in there. And they're all going to be very complex geometry. So here we wanted to sort of simulate, make sure that any of these complex features that we have in a real device, we should be able to simulate it here.
Yeah, thanks for the talk, Professor. So I have a very naive doubt. So I mean, it is known for pipe geometry of a pipe, like for low Reynolds number, the particles actually segregate themselves at some location in the pipe. So I mean, it's Serge Silberberg location. So how does it compare with your simulations? I mean,
so
you have
don't
done.
Want, see, in an actual device, you don't want sedimentation to happen. You're talking about sedimentation particles going down, right?
No, so they actually select a radial location. So they will not sediment.
Okay, so see, those phenomena that you are talking about is a very dilute conditions.
Right, yeah.
Okay, so these are very, very realistic conditions. Okay, so there you are talking about less than 1%. Here we are talking about 40%. So there is a huge 2 orders of magnitude difference between. So none of these observations or whatever work in here. I mean, those are meaningless in a different regime altogether.
Thank you.
Okay, thank you so much.
Thank you, sir, for the very insightful presentation. Actually, I just want to know that beside all the insight that you got from the experiments or numerical experiments, what was the main contribution in terms of OpenFOAM development?
Yeah, so OpenFOAM, so all this is done in OpenFOAM.
Yes.
Yeah,
so
but
there is no contribution from your side in the development part?
So there have been the 2-phase model, there have been again, I mean, in the first phase, single phase, we said that there are certain additional like modification in the local strain rate which was required. So those are the things that, so all this coding has been done in OpenFOAM as such.
Okay, thank you.
And whatever modification in the models which were required, all that was done.
Thank you so much, Professor Amit. Thanks a lot. So we are really sorry for being so late, and it's almost lunchtime, and we will break for lunch only after one talk. So I welcome Professor Bharadwaj in the symposium. Yeah, Professor Bharadwaj is from Mechanical Engineering Department of IIT Bombay. So over to you, sir. You can, yeah, please begin your talk.
Thank you, first of all. Thanks to organizers.
अच्छा वो सिग्नल
Am I audible? Okay, so thank you organizers for giving me a chance here, and Professor Chandan and FOSSEE team. And I have promised Chandan that I will not keep you hungry for long, as we are running late. So this talk is on about development of a IB solver which accounts for fluid, structure dynamics, and heat transfer. Let me just thank the team of contributors to the solver, starting from Atul, who is at IIT Guwahati, faculty, Kundu, Garg, Gaurav Sharma, and these two are project staff who later finished their PhDs from other universities. Avinash is here, Arun. So because of these students' effort, probably we have developed some solver. So motivation of the development of solver. So on the biological systems, for example, elephant ears used to cool his body by flapping of the large ears, penguins, and the leaf, which has just the flutter of a leaf and also the heat transfer, and the last is the biomedical, where you have to do experimentally. For example, cardiovascular flows. It is something, it's not easy to do experiments. What is the flow inside the human heart, and if you have some medical condition and you want to develop a tool for the surgical planning. So the challenges are 3D geometries, their motions, and the large scale structure deformation, geometric and material nonlinearity of the structure involved, and the stability. And if the structures are very light, they are moving back and forth, and their motion has to be captured along with the thin structures or vortices which are being shed at the tip of the structure. So stability is also very important. So you have two choices here, which is developed in the literature. First is ALE method, which is probably you have a structure, you resolve the grid like this, and you track the motion of the structure. So the problem it has is when it becomes large deformation, then the grid will distort. Your numerical solution will become inaccurate. On the other hand, if you have a structure which is just embedded in the Cartesian grid like this, and you have to just track structure and modify your Governing equation such that your solution is still valid, then comes under the category of immerse boundary method. So we focus, of course, on this part here in this talk, and it has a fixed grid, which is in Eulerian framework, as we know of. But on the top of that, there is a Lagrangian grid, and this grid could be also a surface, and that surface could be another grid, finite element mesh, which can be moved under a constitutive law. IB methods have seen a large interest starting from the year 2000s, and you can see how it has grown over the years. That is given in a recent annual review of fluid mechanics paper. Now the origins are very early on, 1971, proposed by Charles Peskin at New York University. So what the idea is very simple. You have a Cartesian grid, and on the top of that you have a Lagrangian kind of framework. So Charles Peskin did it for solid massless elastic fibers. So these massless elastic fiber kind of move in the fluid. Right? They are feeling a fluid force, and that force can be fed back to the fluid by a source term. So that was the modification he did to the Navier-Stokes. Now this source term has to be present in the Eulerian framework, and now it has to convert to the Lagrangian framework. For that you can use a Dirac delta function. So that kernel you can use to convert the force on the structure versus the force density in the fluid. That is the basic idea. And once that is known, you can compute the velocity of the fiber which is embedded, and you can use a Lagrangian framework to track that fiber. Now based on this, there are so many methods have been proposed, and largely you can classify in two categories. One is the continuous forcing, which we just saw. You have a source term in the Navier-Stokes, and you do the discretization based on that and use the kernel to transfer between Lagrangian and the Eulerian framework. You can do it a different way, which is supposed to be more accurate and more involved, which is a discrete forcing. Now you don't use this source term here, but you solve in Navier-Stokes as you do, but you have to account the effect of the boundary. For that you have to classify cells, and you try to apply the boundary condition based on the definition of these cells. So this is my discrete forcing, which is a sharp representation, and this is a diffuse representation of the immerse boundary. Now pictorially you will see, you can think of these two pictures for your Cartesian grid. As you can see, this is my interface boundary, and if I have to plot the force distribution, it looks something like this. It has a region of kind of interest where it kind of transfers the force, and of course then now your solution starts to depend on your grid size. On the other hand, in your discrete forcing, you classify these cells. For example, this is a ghost cell close to the structure boundary, these are solid cells, these are fluid cells, and you have to define some other cells to apply that boundary condition accurately. So let me just demonstrate the application of the both methods, so that just give you an idea. Of course, in one lecture I cannot tell you everything, but I will give you a broad idea so that you can get started. So these are the equations for fluid flow and heat transfer in their generic form. So I will just consider the heat transfer because it is being the easiest, and these are the 3 boundary conditions we can use to see the demonstration of the 2 types of the IB methods. So I add this Q, the source term, on in my energy equation, and this can be put in terms of a flux on IB using the Dirac delta function. This is in continuous framework, but now I make it discrete. I can use a modified Dirac delta functions proposed by Charles Peskin and many others, and the famous one is so called 4-point delta function. So this is the definition of the discrete Dirac delta function. Now this is the definition of my flux at flux density which goes in the energy equation, and this is the flux at the boundary. Okay. Same way that I can define a conversion between the temperature in Eulerian framework to the Lagrangian point. Now if the boundary condition is such that I am given the flux on the Lagrangian boundary, let us say I have a body which is in a fluid and it has a given flux. So it is very easy, you just put the flux, put the source term here, solve it as we will do, make sure your grid is refined, and you get the solution. But now if the temperature boundary condition is given in form of Dirichlet type or let us say convective, it becomes slightly involved, that you can see in the next slide. So when you are given those boundary condition, you first solve for a predictor step where you predict a value, then you have a prediction T star. So I just first solve without this Q, I predict a value T star, and then I want to correct it with Q. So typical predictor corrector step. I have not shown the predictor part. Now this is the corrector step. In the corrector step, I will consider Q. So this Q is that source which is present because of the immersed boundary. Now this is the boundary condition which I am given with. This is the Tk wall. So Tk is my Lagrangian point. Now I can define this boundary condition in terms of the Eulerian points using the Dirac delta function. Now you can substitute this Tn plus 1 values which is in Eulerian framework to this boundary condition, which actually gets me a equation which has my boundary conditions and my predictor value which I have already found, and this point, this flux which is still unknown, but I can use this equation, the sourcing, to put it in this to get a algebraic equation like this. So this equation, the left hand side is known because this is my boundary condition, and now what I need to find is just Qm's. This is actually the flux at the Lagrangian boundary or your structure. Now I can solve this Ax is equal to B system after I am done with the predictor step, and once I solve Q, I can obtain small q and then I can find the temperature. So it is not that hard, but you have to follow these steps for this type of boundary condition. Now further, how to apply the convective boundary condition? Now you have to basically modify this value. You actually do not know the flux, that is what you are actually looking for, but you can say that there is a virtual boundary Vb where you can define certain points which are away at a certain distance h from your boundary, and you can find that wall flux, right? And that flux you can put it in convective boundary condition, and now this convective boundary condition can be used, put it back here, again you can solve Ax is equal to B system. So it involves an extra step to solve this equation when you use a continuous forcing inverse boundary method. And let us go now to the discrete forcing. So I will skip many things here in the sense that one thing is required to identify these cells. So there are algorithms like ray tracing method and others to figure out which are solid cells, which are fluid cells, and the cells ghost cells which are important and close to the boundary. So ghost cells are important, which also appear in my discretized equation for the fluid. Now it is something like method of images. The ghost cell is a fictitious cell, but it appears because I have the discretized form of equation in Eulerian form. Now, ghost cell is something which I need to worry and find the equation which I can solve together with my governing equation to solve completely for the flow. So, first I define ghost cell and then a cell called image point, IP. So, I draw a normal which intersects at this boundary, which is called boundary intercept, and equal distance I travel in the fluid, I get IP, which is image point. So, the IP is now fluid. I can use a bilinear or trilinear interpolation to figure out its value. This is from the fluid. Okay. Now, I have boundary condition given. So, if it let us say Dirichlet type, simply by method of images, TBI is the sum of IP, which is image point in the fluid, plus ghost cell, right. TBI is known to you. If it is Dirichlet, let us say temperature, it is known to you. So, this equation in conjunction with your discretized equation Navier-Stokes can be solved together and iterate for TGC. You can find TGC ghost cells, and then you can solve for the temperature field. So, this is easier and more accurate, and you can actually see you can achieve a second order accuracy near the immerse boundary, which is not the case in the continuous forcing. Now, other boundary conditions can easily be implemented. Let us say you are given a flux boundary condition. So, simply flux is the sum of the difference of IP minus GC divided by delta L, which is the distance between your IP and GC. Now, in that case, the equation which I need to solve together with Navier-Stokes is this. So, these two equations can be solved to figure out your solution. Okay, now we have solved for the effect of the immerse boundary. Now, these boundaries can also be moving, and that is more complex in the sense that it will involve the coupled solutions of the Navier-Stokes and the constitutive law. So, this can be done in two ways. You have a single code where you account for the effect of both, or a partitioned approach where you solve separately. You solve a structure dynamic kind of solver and then fluid, and then you couple them together. This is actually known as partition approach, and of course, they have pros and cons. I will more focus here on the partitioned approach, and this is something we have implemented. So, this is our in-house flow solver, and it is second order accurate finite difference method based solver, and we use a ghost cell sharp representation of the immerse boundary. The structure solver is an OpenFOAM, the Tahoe, and it also can be implemented in the OpenFOAM in the sense that this is a separate entity. So, this structure solver can be solved with any fluid solver. So, now I can couple them together. What I need to worry about is how you apply the boundary condition. So, every time step you have to calculate the fluid dynamic forces from the flow solver in the presence of immerse boundary. Then you go to the structure solver and then see how much displacement you are getting, and then you go back to the flow solver. So, this has to be consistent with the kinematic and dynamic boundary conditions, which are no slip on the solid surface and the pressure balance on the solid liquid interface. If you respect that, then you can achieve this convergence. So, here we are doing flow computation in Eulerian grid, and the solid solver we are solving in the Lagrangian framework. That is something has to do with the solver, which is this one Tahoe, which solve things in the Lagrangian framework. So, we use two different solver to couple them together and then test it. So, here is the convergence of the two solver, how you can achieve, and this is the case where you have a body which can oscillate in the flow, and you have to make sure that you capture all the flow. So, you have a given conditions, let us say plate which is deforming with the flow. You call the fluid solver and you figure out how much it has deformed based on the pressure it has or the velocity field it has. Now, you have gotten a pressure field, then you call the structure solver and see how much it is deforming. Now, the question is, it has deformed something and we have a pressure field, but the two boundary condition may not be consistent. So, you have to go back again to the fluid solver and check whether that pressure field is consistent. So, basically you iterate this whole process until you find a convergence. So, the convergence criteria could be the displacement of your body or the velocity, and you can also under relax for stability reasons. So, this is something more involved and take more time. So, this is the algorithm here. You calculate the flow and pressure, then forces, then deformation, then you check the residual. If residual is good, you just converge. If not, you can go back. So there are two ways you can do this step, in the sense that you can still accelerate this process by something called dynamic under relaxation. So the relaxation factor cannot be just constant. You can make it bigger if the residual is larger, or it is converging basically faster based on so-called Atkins method. So that also we have implemented and tested. So I'll show you a result and show you some of the things we have done with the sharp interface, immersed boundary plus the partition approach. So this is a problem proposed in 2006 by Turek and Heron. It is a kind of a benchmark for fluid structure interaction. So there is a cylinder which is solid and is stationary, and there is elastic plate on the lee side which can deform. And once you start the flow, it should sustain those oscillation which are due to the shaded vortex in the downstream. And we can compare its displacement or amplitude and the frequency. So this is the motion of the plate. You can see it starts to deform, and then it will sustain certain motion, and what we can compare is its dynamic of the elastic plate. So now you can see it sustained, and what is of interest to me is this amplitude and frequency if you ignore the initial transient state. So you can see it compares well with the published data. Now this is a test for the dynamic under relaxation. So this red curve showing okay, I am using a constant under relaxation, and this is the maximum allowed. If I increase it, it may crash my code, but let us say I use Atkins, I can actually speed up by the factor of half based on actually the problem. So some cases it may converge faster if the non-linearity is lesser, but some cases it may take larger iterations. So these are actually sub-iterations. These are iterations not in the fluid or in the structure. These are on the top of a global iteration. So we have a solution for the fluid, we have a solution for the structure, and the top of that we are converging them together. We have also tested very thin plates, and this is much thinner than the previous one, and you can see the grid here, probably not, but it is very refined, finite element method being used to simulate the motion or from the structure dynamics point of view. And this also sustains a motion, periodic motion, and we have compared the frequency and the amplitude. Now what we explored next is thermal augmentation caused by these vortices. Can we use this secondary vortices, which is kind of a passive motion, to improve the heat transfer? In the same problem we tested. So this is the result, and now you see this plate which is moving and creating vortices. These are being hitting at this wall, and then it is improving the heat transfer by seeing the isotherms here. So this is vorticity, this is the isotherms, and these are u and v velocity, and this is the plot of the Nusselt number on these two walls. A peak means you have improved the heat transfer. So you can see in the animation as the vortices are being shedding, and then when they are hitting the wall, they are improving this heat transfer, and as you go in the downstream, they starts to die down. Now I can compare it in a controlled way with a channel, with a stationary cylinder, rigid plate, and a deformable plate, and you can see that in the deformable plate, the mean Nusselt number over time is much higher, larger than the other two cases. But it also increases the pressure drop in the channel, so you can kind of estimate that as well and figure out efficiency or how effective is this method as compared to the other method. So it is better to have a deformable plate rather than just a stationary cylinder. That's what our data is showing. You can see the efficiency kind of increases from cylinder to rigid plate to the deformable plate. Okay, we have also tested our solver for vortex induced vibration, a cylinder which just oscillating in a y direction due to the transverse forcing or the shaded vortices in the downstream, and this is the region lock-in where it achieves the highest amplitude, and that our solver captures very well. With the last physics problem, we tested the augmentation by a D cylinder, and why D? Because it oscillates at very high amplitudes and scatter those vortices around, and those are of high intensity, so we are hoping that it will improve the augmentation even further. And this is the movie for D, which is stationary, and this is the movie for moving cylinder, which is close to galloping, and all these vortices which are being hitting, and you can see this peak which are helping us to improve the heat transfer. And this is the comparison showing D section cylinder is much better as compared to other cases. Okay, I will close here within this brief presentation. So, I have demonstrated a FSI solver which can be used to simulate these complex problems, and we have benchmarked this against the known solution and also used it for understanding the heat transfer. All right. Thank you, and I will invite any questions you have. Yeah. Go ahead. Yeah, you can easily resolve, but you have to need a very fine grid close to the immersed boundary.
Because the background mesh is fixed, right?
Right.
And then how does because we need the resolve kind of mesh around the solid near the boundary layer.
Typical estimate is you need around 10 points in the boundary layer thickness. So whatever Reynolds number you have, you can estimate that, and then maximum Reynolds number, and based on that you can just see to have a minimum grid size which can have 10 points in the boundary layer.
Okay, so the background has to be refined.
Background has to be refined because it is fluid.
So it cannot be tracked somehow using, for example, dynamic mesh?
So we do have a dynamic mesh.
Oh.
So it can go anywhere, right?
Okay.
But all the regions where it is going, you have to have that refined mesh there.
Oh.
So that becomes more challenging if the deformations are very large. Then you have to refine a big box.
Yes, exactly.
Rather than the stationary body.
Exactly.
And that's exactly the challenge with this plate problem I showed you.
Yeah. It happened just, I'm also working on the same problem.
Oh, okay, that's good. Good luck.
Thank you so much.
You are on the right problem.
Right. Thank you so much.
Yeah.
Sir, so thank you for the talk. One thing which I am thinking of is the direct comparison of the body fitted mesh versus the IB mesh. So, you know, solid body fitted is conventionally accepted and it is kind of widely being used. What are the, I need to just summarize the points. What are the limitations of IB compared to this? And secondly, what are the computational time enhancements if we are using IB in its strong regions compared to body fitted?
So IB will deteriorate at like let us say very high Reynolds number, especially the continuous forcing. Then you start not to have this capturing this no slip boundary condition. But discrete still works at high Reynolds number. As compared to ALE, I think the advantages are it can capture say complex surface, right? When you develop ALE, let us say you have this my face, right? It has, because I have done this problem, that's what I am saying. So we have a face and you are facing a flow, right? So you have all these features, eye, nose and all this. So you have to capture that by your 3D mesh, right? So ALE, it may happen so that you may have somewhere a bad mesh and it will give you a problem. Right. So the good thing about IB is you can capture all these complex 3D shapes, right, which are immersed in the flow as compared to your IB method. So that is one advantage, and regarding the time, I think it depends on which solvers and schemes you are using. So it's a little subjective question, but in general, I don't think there is a large difference between the computational time. One thing is with IB is, especially what the version we are using is when you refine, right, we have not using the adaptive mesh. It means that we have to refine everywhere, right? So we use a Cartesian mesh. So let us say the box becomes bigger, so where the body is moving, so you need a bigger number of points as compared to let us say adaptive mesh, where you can just refine where it is going. So that is the advantage and probably future work we can do. All right. I hope it answers some of the questions you have. Yeah. All right. Thank you.
we wait for a few more minutes? Let's start, yeah, otherwise. Should I start? Or where are the Evans and they are coming? Or? Okay. So should I start? Okay. All right. Hello everyone. So basically today I will be presenting some of the ongoing work in my research group, and so as I've already told that I lead bio-inspired fluid structure interaction group in the aerospace engineering of University of Birmingham, and we are interested in problems particularly in biolocomotions for different aerial and underwater vehicles, apart from other branches that we are interested, such as biomedical. I'll talk a little bit, but mostly today I'll show you how we use or build frameworks using open source tools and softwares to solve this kind of coupled problems. And here by coupled I mean mostly we'll be looking into the coupling between fluids and structure. So because we are already behind the schedule, I'll keep it very short, but rather than going into the physics of the problem, I'll try to highlight more on the computational side and what kind of framework we are using within the open source CFD code OpenFOAM. So I have been using and developing OpenFOAM since 2014, starting from the start of my PhD. When I get this code, which is a open source code written in C++, and my advisor just told, okay, look into the code and see what we can do, how we can modify, and how we can develop new features or add new complexities within the code. That was the approach. We have come at least 1 decade after that, and now the approach is mostly people try to go into user mode, that it's almost like another software they call it, which I basically don't agree with. It's not a software, it's a bunch of codes and libraries that you can look into and see the governing equation build and develop. So that's with that approach, I think that will be my main message, that OpenFOAM is not a software. It's a bunch of C++ code with lots of different libraries. So understanding what is written inside is very important if you really want to develop new features and complexities which are already, it does not exist, and that's the main difference between commercial software and having an open source code. So with that, mostly the works I'm going to present are done by my student, my master student Paras, who is in Georgia Tech now, and 3 of my PhD student, Hiba, Yukesh, and Arjun. And I wanted to start with a summary of the different things that we are doing. One thing is basically we are very interested in flight of small natural flyers such as insects and birds, and one of the fascinating flyer is butterflies. So we are trying to understand the swarm aerodynamics of butterflies and how we can build swarms of micro drones based on that. And so we use integrated overset and immerse boundary approach for solving this, but I think I will not go into details of that. But for now, we are only simulating a swarm of rigid flyers, which in future we are trying to make it with flexible wings. But on the other hand, one of the other project is avian-inspired morphing wings for aeronautical, microaerial, and unmanned aerial vehicles, which I'll talk a little bit more depth about and will show what framework I use. Apart from that, we solve a lot of, for example, the undulatory motion of the fish that I will touch upon, how we can use different kind of overset meshing to incorporate such large amplitude motions. I will also touch upon a problem where we are designing a flexible nozzle based, which is mimicked from the funnel of cephalopods, for example squids, to generate vortex rings which can augment the thrust for underwater propulsion. And we also are doing different kind of vertical axis wind turbine application inspired by seed pods, which are auto-rotating, and we are trying to exploit that auto-rotation. I also study as part of my postdoc project flying of passive particles and passive seeds such as dandelion, which has a very interesting structure of porous pappus with a umbrella kind of structure where the center of mass is hanging below. And we want to study if we can design micro drones, swarms of micro drones which can fly passively without the need of a power, like micro aerial vehicles or unmanned aerial vehicles. Now, with all of these applications are mostly done using OpenFOAM, or not using the ready-made solvers, but using the solvers and developing other features within that. But of course, one of these problems where we are studying butterfly swarms, we have our own immerse boundary method codes, and we are now in collaboration with Professor Somnath Roy's group in IIT Kharagpur. They also have an immerse boundary code. We are trying to accelerate it to multi GPUs and incorporate overset mesh approach to solve this problem. So quickly, the first part that I showed, which is morphing wings, which is passively morphing wings, or where the gust imposed of the wing deforms the wing. And we solved this problem in a two-way partition coupled approach using IQ and ILS acceleration scheme, which is very similar to what Professor Rajneeshwar was showed at Keynes relaxation. It's another type of quasi-Newton methods. And we use radial basis function, thin plate spline interpolation for data mapping at the fluid and structure interface. And of course, the flow solver is within OpenFOAM. We use a finite volume approach. And for the structure, we use a finite element open source code, which is Calculix. And we use implicit classical Newmark method for solving the structural part. Now, I'm not showing you the governing equation, but of course, incompressible Navier-Stokes equation is used, and on the structural side, we are using neo-Hookean hyperelastic material because we want. Quickly, I'll show you what we mean by two-way partitioned approach, loose coupling approach. Here, basically, the fluid solver solves the mesh. It moves the mesh and calculates the aerodynamic forces, transfers at the fluid and structure boundary. That forces get transferred to the structural solver, and by using finite element, we calculate the displacement for the applied aerodynamic forces, and then it solves this in a two-way coupled manner in a staggered approach. But because it's a strongly coupled quasi-Newton method, we check for the accuracy or the tolerances for both the fluid and the structural solver in every time step. Now, we use a parallel implicit coupling scheme which is much more accurate than explicit schemes, and we use different type of sockets for communicating with different nodes, multiple nodes of a CPU based architecture. And because this is within OpenFOAM and Calculix, this is not GPU accelerated, so we solve it using CPUs. And we prefer the radial basis function interpolation compared to the projection based approach such as nearest neighbor or nearest projection, because this gives us the flexibility of not having a direct mapping between the solid and fluid nodes, because it is not always possible for complex geometries to have the same nodes at the interface from the solid side and the fluid side. So radial basis function actually allows us to interpolate at the boundary with two different mesh sizes and two different nodes from the solid and fluid. So I will just demonstrate very quickly what problems we are trying to. So one problem we are solving using this framework is covert inspired flaps. So it has been demonstrated experimentally recently that if we use flexible flaps which acts like secondary feathers of the birds in low Reynolds number applications such as micro aerial vehicles or unmanned aerial vehicle, they can actually augment the propulsive efficiency quite significantly. So we started understanding what happens when we actually apply very thin flexible flaps at the leading edge, particularly because this delays the shading of the leading edge vortex and its corresponding interaction with the trailing edge vortices. And how does that delay the stall characteristics? So that's basically one of our main research question that we want to understand. And of course, it's a very rich dynamical problem. There are multiple frequencies involved. and the correlations with those frequencies with the natural frequency of the flap and the vortex shedding frequency is a very interesting question that we are trying to understand. And in the next step, we want to understand the next phenomena, where actually in real life we have multiple such flexible flaps arranged in different optimized configuration to give us the maximum aerodynamic benefit. And the underlying phenomena that affects this physics is the synchronization, which is also a very rich nonlinear dynamic phenomena depending on the frequencies involved in this kind of flaps. So we are asking more futuristic question: what happens when the stiffness of these flaps from leading edge to trailing edge are different, which is in reality in bird's wing, which they are not the secondary flaps and the primary feathers, they are not of the same same flexibility, and the flexibility also varies from leading to trailing edge. And that's the question nobody has asked yet, because most of these problems for the benchmarking and everything, people have just started flags or a rectangular thin plate, which is easy because of its geometry, but actually in real life, if we want to mimic the nature, that's not the case. So our next problem that we asked, that if we see different species of biological flyers such as falcon or barn owl, we see different cross-sectional shape of the wings in different span-wise direction. So which basically demonstrate the variability of the flexibility along the chord-wise direction and as well as the span-wise direction. So we scanned the high-speed videos of these wings of these birds, and we, in collaboration with one of the colleagues, we extracted the coordinates, exact coordinates of these birds' wings, and we wanted to see if we can simulate that when it subjects to gust, and what happens and what is the role of this kind of variable flexibility is in mitigating the gust. So we tried different kind of canonical gusts such as ramp gust, rotational and translational gust, etc. And in this animation you can see the same gust response for two different flexibility case. And you can see for KB, which is a non-dimensional bending rigidity, I am not describing everything for the interest of time, but it denotes the non-dimensional flexibility, and if it is 5, it is way more flexible than KB equal to 50. And it gives us very, very interesting physics, and it has lot of different parameters that we are studying. But I just wanted to show you that this kind of very high amplitude flexible problems could be solved very robustly with high accuracy using open source codes. Okay. And the physics I am not going, but we have studied the trailing edge displacement and its corresponding correlation with the lift characteristics and the efficiency, and what happens when we increase the severity of this gust from a very smooth gust to a very sharp gust, how does the aerodynamic characteristics change. And then we did the same thing for a translational gust, and we are trying to understand what is the specific mechanism in terms of vortex shedding which changes when we change the mode of kinematics from plunging to pitching. And we studied it for example, this is an owl section. So from a falcon to owl, and we are also comparing the response of both of these. And ultimate goal of me, the research question is that if we take 10 different species of this wing section and we want to design an unmanned aerial vehicle, what is the most optimized section? So for that we are using different data driven optimization techniques such as Bayesian optimization and other different evolutionary techniques to decide what will be the most optimized wing shape for our engineered aerial vehicles. And we are also studying the vortex shedding and convection of the circulation, and what is the convection speed of the leading edge and the trailing edge vortices, and how does that affect the aerodynamic characteristics. So the second, so this was a completely arbitrary Lagrangian Eulerian approach, which has limitation of negative cell volume. So when we basically deform it with a very high amplitude, your simulation diverges, because you are deforming the mesh, you are compressing the mesh at some place, and you are expanding the meshes at some place. So to avoid that, we then we are actually developing a modified overset approach, which then is not an arbitrary Lagrangian Eulerian approach. And by overset approach, it means that we have multiple disconnected mesh elements, and we interpolate the data at the overset patch, and which allows us also to prescribe this deformation. So till now we were doing FSI, which was passive deformation, but in most of the cases these biological animals, they have a hybrid way of deforming their wings. Sometimes it is actuated, sometimes it is passive, depending on the surrounding scenario they change their response. So to incorporate that, for example, this is an example where we deform the wing by a prescribed equation in the leading edge and the trailing edge as it plunges. So that kind of interesting scenario, and it is completely closed formed. So I can decide how to actuate this kind of deformation, and then when we subject it to FSI, we have a hybrid response. So that's basically, it's a very complex scenario, but that's what I want to study. And this is how the mesh moves and the mesh elements gets actuated with the given equation. So which can be easily then given into undulatory fish motion kind of equation, where we can decide what will be the phase difference between the amplitude and the wave frequency, and we are also studied that, but we then modified in terms of computation. This is one way where it is body conformal mesh, there is no overset, and it also has this similar negative cell volume thing. So to avoid that, we modified this into this kind of overset approach, where we actuate every mesh point with the given actuation. So because of that, we do not have the issue of any negative cell volume, and we can actually simulate any type of actuation, be it periodic, chaotic, any type of amplitude and frequency. And now we are testing that for 3D. So ultimately, when you can see, this is a owl wing volumetrically reconstructed from biological data, and we are twisting it actively, and then when it's subjected to gust, it passively also moves, so that we can study the hybrid phenomena. And similarly, we can also study the 3D fish motion in that respect. And this is one of the vortical signature and the deflection envelope for the 3D fish that you see. And this is for the 3D wing. Okay, I'm not going into the physics of it, but it is possible to incorporate. Now, in next 2-3 minutes, I will just show you the most interesting application, which would take 1 hour to explain the physics. But all these cephalopods, you can see they have a funnel, starting from squids to jellyfish to all the marine animals. And what they do is they actively as well as passively actuate these funnels so that there is a wave propagation, and that ejects vortex rings, which is of most interest to us fluid mechanicians. And that vortex ring actually creates a very significant thrust on the forward motion, and that is what we are interested for designing underwater vehicles. So you can see this biological experiment done in Stanford by one of the colleagues, William Gilly. You can see the way they actuate, and if you just, it is not tethered, it just goes on the opposite direction with a very high amount of thrust. And so the basic fundamental phenomena that I am interested in is to understand this wave dynamics. How do you change this wave dynamics into highly flexible nozzles, and how does that correlate with the vortex dynamics, with the vortex rings that is generated. And so we modeled it using the same framework, FSI framework, and you can see how complex this is. That so to accommodate that, we had to really modify a lot of different CFD schemes and the coupling algorithms, because it's not easy. And so you have the nozzle mesh, and we had to really fine tune how much region of the mesh will actually deform and how much of the mesh will remain rigid in that sense. But it is possible. These are all done using OpenFOAM, and we are working on it, and we have validated it with experimental values of the wave, non-dimensional wave speed. So we have quite high confidence in it. And we have also studied the wave dynamics of it and its correlation with the vortex dynamics. I'm not going there, but we'll show you the effect of flexibility. How does that affect? So as you go here, this EH is a measure of flexibility and this, and you can see that for the most highly flexible nozzle, for the same input and input, we get very different output. Instead of one vortex ring, we get multiple vortex ring, and which drastically changes the thrust characteristics. And with this, I will end my talk, where it is more complicated. When we attach it to actually underwater vehicle, we have a rotary propulsion. So it's no more a pulse jet, but we have very complex 3-dimensional wake which is going around this flexible nozzle, and we are still working on it, but I can say that this is the most complex simulation I have done till now, which is fully two-way coupled and subjected to a completely very complex turbulent spiral wake. And as you can see that these mode shapes are very, very complicated. But all these things are possible using these open source tools, but there is no ready-made solution. You have to understand the underlying CFD and equations and modify accordingly. So if you want the solver for me to give you, you can run this case, but you won't be able to run the another case because there is no ready-made solution. All right, thank you very much. I'll end here. If there are any question, you can ask me, else I'm here till afternoon, so you can discuss with me anytime. Yes. No, this is the FSI cases that I showed. They are all arbitrary Lagrangian Eulerian approach, OpenFOAM calculus coupled by a quasi-Newton method. The immerse boundary and overset I have not presented. That is for the swarm of butterflies. So we are currently simulating a case where we have hundreds of butterflies flapping together, so which we cannot solve using CPUs. So we are using multi GPU nodes to solve it, and that's the code that we are accelerating. It's an immerse boundary plus overset approach, but I have not presented that here.
Okay, so
whatever I presented are all using OpenFOAM and modified OpenFOAM solvers.
Okay, I understand. For the cases that you've presented with the arbitrary Lagrangian Eulerian
yes.
framework,
but an overset. And the overset.
And overset.
Yeah.
Okay, so you've used overset.
Yes, but within OpenFOAM, not with immerse boundary.
Okay, I understand that. So basically there is no immersed boundary in OpenFOAM?
There is. I use so it is in foam extend.
In foam extend.
Yes.
I mean, in this regard, it's basically developed already in OpenFOAM
yes, it's there. But immerse boundary had multiple different classes. Continuous forcing to discrete forcing. So it depends which class of solver you are using, which Professor Rajneesh Bharadwaj presented.
Sure. And how did you manage the large deformation for the ALE method, or was not that much large?
No, it was large. As you said, the last problem it is ALE. Yes. But one way to use overset for the feast motion that I showed and 3D. That is one way. But the last problem using overset, we have not yet coupled with fluid structure. We are working on it. Okay. But the last problem that I showed, it needs lot of modification as per your fundamental CFD knowledge. So you have to keep changing the schemes, using higher order schemes to get to the convergence, etc. So we managed to get to it with using ALE, but it's not one solution for all the problems. So for your problem, you have to optimize your CFD schemes.
Okay, and for the solid part, you also use the FEM method?
Calculus,
completely.
And hyperelastic formulation, Neo-Hookean formulation.
There was no trial of finite volume based solid dynamics?
No, there is a coupled solver called Solids for Foam, and tomorrow our research assistants will give a training on that if you are interested. Yeah. So Solids for Foam is a formulation, is a coupled code which is almost monolithic. It's not partitioned. It has the finite volume fluid code and finite volume solid code, and they are coupled. But I have not used that. So this is partitioned approach where I have two segregated solvers for fluid and solid. But you can also do it using that. I have not done it yet.
Sure. Okay, thank you.
I have a question. Yeah. So in your GPU, what you told under development, so OpenFOAM doesn't have GPU at present.
Not
right?
yet. So there are efforts going on. There is a ExaFoam project in European Horizon project, but till now they have done it for very benchmark problems such as stationary bodies with the motorbike tutorials, which are most benchmark based. But for moving body problem, I have not seen any implementation in GPU yet.
Yeah. And another follow-up question. So when you do IB for multi-body, like multiple functions, how do you validate those things?
You mean, so basically, of course, if I am doing 100 butterflies, I do not have any experimental data. So we validate it for a single butterfly case, and it's a valid question that when we have multiple together, we check, the conservation, flux conservation, mass, and numerically we verify it, but I have not yet thought of how to validate it because we do not have any experimental data for a swarm. But we have validated it for or we are validating it, it's an ongoing work, for experimental data with a flight condition of a single butterfly, let's say, with different kinematics. So the motive of studying butterfly is that it's a very special animal which does chaotic trajectory. So all the other animals, when they fly in swarms, they follow a regular trajectory, but butterflies never follow a certain path, and they have different kind of kinematics which are very interesting and not observed in others. So it's a valid question. I have to think how to validate in swarm. I have not done it yet.
Thank you.
Okay, I think for the interest of time, you can discuss with me anytime I'm here, but let's go to the next talk.
So we can go ahead. We can go ahead with the next talk session by Professor Samir Jadhav. Professor Samir is from Chemical Engineering Department of IIT Bombay.
Sorry.
So good afternoon. So I will be presenting a work that was done with my PhD student Deekshit, who recently graduated, and the work is on Brace's paradox and flow switching in a microfluidic network. So Brace's paradox was found by, as the name suggests, Brace, especially for traffic networks. So typically what is seen is that if there's we see here a start and an end point, and if there are two branches, so one going through A, another through B, and typically what one would expect is if one has a superhighway between A and B, that would allow for more efficient traffic movement, faster movement. However, it is seen that under certain conditions that is not so, it becomes inefficient compared to the case where this link is absent. Later on, this particular paradox has been observed in mechanical systems, electrical systems, even in biological networks. In 2019, in a Nature paper, it was shown by Case et al. That this particular paradox is observed in a microfluidic network. In this, there are these two branches or two streams, and then there is this arm over here, and where the inlet is, these two arms, and at the outlet there are these two other arms, L4 and L5, one of which has some obstacles, and it's observed that as one increases flow, it happens that in the absence of this linking arm, whatever is the flow, at a certain flow rate, the flow in a network where now you have this linking arm, the flow becomes less than that in the unlinked unlinked network. So that is primarily because of this dissipation which occurs because of inertial flow, which shows a higher dissipation compared to viscous flow, and because of which we see this effect. So in our case, we simulated it using COMSOL, and basically we had these in 2D and 3D cases. 2D case, the Reynolds number is defined here, whereas in 3D we have the width and the height of the which are the two cases of the or that basically the two cross section of the microfluidic channel. So we were able to simulate the case by of that was there, and you can see here at a pressure difference across the network of 600 Pascal, flow is from top to bottom, whereas in this case there is flow from bottom to top, so there is flow switching. So what our objective was to basically see how we can look at optimal designs or obstacles that will allow us to then see this earlier at lower Reynolds numbers. So just for the understanding the results, we have measured the hydraulic resistance, which is just the pressure drop by flow rate. Then we have a difference in hydraulic resistance, which is the obstacle channel minus a similar channel without obstacles, and we have the normalized value, and finally we have what is known as the relative or relative normalized hydraulic difference in hydraulic resistance, that is this N delta HR. So that basically is at a higher Reynolds number versus that at very low Reynolds number. So the idea is to find obstacle shapes which have this particular value maximized. We used several such designs. They don't show very clearly, but we have the spherical obstacles, we have these rectangular slits, and various arrangements. Here we have a single sphere. We have 2, 3, and 4 spheres, but the fractional blockage of the channel remains the same. And the same case we have for these slits. And for each of these cases, we measured this Rn delta HR values, and we saw that for circular obstacles, the value was around 2, whereas in case of rectangular obstacles, we could get as high as 10. So obviously we stuck to these rectangular obstacles. We also looked at the effect of the width of these obstacles, and as you can see here, the values are highest as we go lower in width. We decided on 6 microns because lower than that are difficult to realistically fabricate. So that is the one we have used. We also had this kind of alternating rectangular obstacles as well as we had the case where we had an obstacle in the center and then the one at the ends. So this is the case where the walled obstacle followed by an unwalled obstacle, and then we also had the case of the non-walled obstacle followed by the walled obstacle. And the one with the first case is the one which gave us a larger value. As you can see, it's around 6.5 to around 5.5 here. However, this alternating obstacle case gave us much higher values, and we used those, and we increased the distance between these obstacles, consecutive obstacles, and also the height of these obstacles. And for various cases, we measured this Rn delta Hr, which are plotted here for this zoomed in case, and the maximas of those we again plotted, and that gave us a value around 330 micrometers for the height and 225 for the distance between the obstacles. So we did that for a single obstacle. Here we have a stack of 2 obstacles, then 3 and 4, and we measured this Rn delta Hr in each of these cases. And obviously, the more the obstacles we find, the larger value of Rn delta Hr. What we noticed was also that a flow is steady in case of 1, 2 and 3 such stacks, but when we have 4, then for the same Reynolds number we start seeing fluctuations because of chaotic motion. As you can see here, this is for 200, Reynolds number of 200, it eventually becomes steady, whereas here we see some chaotic motion, vortex shedding. We basically also did these what are known as Darcy and Forsheimer coefficients related to the relationship between pressure drop and flow rate. So the Darcy's coefficient is for the linear case, and for the quadratic we have the Forsheimer's coefficients. We measured these. We also carried out these for 3D microchannels, and in that case we see that this Rn delta Hr increases as the depth is reduced, and when the depth is increased, it then asymptotically moves to the 2D case. So, so we optimized the gap for these cases. We also looked at basically these are plots of the flow, and as you can see, there is the motion is sort of a vortex forming here, and a similar one in the cross-sectional case we see here vortex formation. So we can or recirculating zones, and because of which we see this nonlinear behavior. So this is for the 3D case. We have calculated the coefficients. So the idea is to calculate these coefficients so that we can then look at networks and then measure, once we know these relationships between the pressure drop and the flow rate Q, then we can study these cases. So this is just the resistance in the channels. In our case, we use the square channel, and in terms of equations, these are the equations which relate to the flow rate with the pressure drop in each of the branches of the channel. And these are just solved analytically using Mathematica, and we get expressions for flow rate Q5 in the Q5 is the flow in this link channel. This QT is the Q total flow rate across the network, and that is in the presence of the channel, and this is in the case when that branch 5 is absent or the link channel is absent. So these are various expressions for each of these cases, but so what we see here is when we solve those equations as a function of the pressure drop, we see that there is flow reversal in the case of the link channel over here, and at the same pressure difference we see also there is a reduction in the total flow rate across the network also shows us that that changes sign. Yeah, so that is basically what we were looking at in terms of this, and then what this allows us is, this is a simple case of a network, but this allows us then to model networks and then look at what would be the flow rate in these networks, and then one can go ahead for larger networks. You don't have to simulate the entire thing, but using these expressions one can then study such large microfluidic networks. So this is other work which long back during my PhD I had looked at simulating white blood cell flow, rolling in blood vessel walls. So this is a movie which shows experimental visual of a white blood cell rolling, and we used immersed boundary method to do the same, and I'll not go through the entire equations, but basically we used for the fluid flow and the fluid structure interaction immersed boundary method, and then receptor ligand interactions were using a stochastic model. So you can see that it's not smooth rolling, there's a stop and go motion which is seen also in real blood vessels. So we also were able to look at collision of capsules in flow using the immersed boundary method. This is just a plot of the pressure variation during the collision, and one can then measure the contact area, and all of this is important because the work that I was looking at is basically how these cells aggregate due to collisions in shear flow. So and one can see that there is a optimal contact area with the flexibility of the membrane. If it is too flexible, then we do not, this contact is not there because of an increased lubrication effect, because they are too deformed and do not come close to each other. So same goes to the contact duration, that also shows an optimal value, after which and these can then be used for calculating such the collision efficiency between various capsules. So with that I come to an end, and just acknowledging Dikshit, who is my PhD student, and Costas and Chuck. These were my Costas was my PhD advisor, and Chuck was a postdoc advisor, and I'm happy to take questions. Yes.
What's the application of the method you've showed us?
Yes.
Where is the application there?
It's basically if one has to study large networks in terms of microfluidic networks, then looking at which branches there will be flow, and it's also, as you can see, a function of the pressure drop or the Reynolds number when you're looking at flow. So that will allow us to see in which branches you will have flow and where we will see flow reversals.
Okay, so in these channels where there is obstacles, where we put obstacles, like there is some optimization operations
right,
there,
right.
and then that give you a better kind of better flow when you put the obstacles.
So the idea is to have some kind of an internal switching. Like suppose you have certain set, you design a microfluidic channel where at low flow rates you would want flow in one direction, and then you want to switch. Now you can design your channels in such a way, knowing these resistances, that you just have to change the the main flow rate. Right? You don't have to individually have control over each of these channels.
Okay. Yes, yes.
So that is the basic application.
Sir, I am having a quick question. So actually from console you have calculated the flow rate in the network, then use those value to
in
solve
the channel.
In the channel.
See, for a channel without obstacles, we can theoretically calculate. But when there are these obstacles, we want to optimize or maximize the relative normalized hydraulic resistance, a mouthful. But the idea is that where you will get this nonlinearity the quickest and the steepest.
But in your analytical solution, you have given the feed from the console results for the branch.
So the Darcy's and Forsheim's coefficients we have, and then for the network we then solve those equations for this network. Now in the case of a large network, we may not be getting these analytical solutions. There one may have to solve them numerically.
For the deformable capsules, blood cells, what are the boundary conditions when it was rolling on the
surface? So in the immersed boundary method, what we did was we had all periodic conditions, but we put sort of it's an elastic surface on which it is rolling. So it's a bed of springs with a much higher stiffness compared to the elasticity of the membrane. So the membrane is more elastic.
I see. And for the collision of these two capsules, you mentioned the capillary number 0.04 something. So what are the typical, let's say, computation time and size of the simulation box?
So it's like I've done it for 1024. I mean, you do 2 to the power n, so 1024 by 1024 by 1024. So that was done way back in 2000, and that was on an IBM supercomputer using OpenMP 16 cores, basically.
Okay. Nice, thanks.
Yes.
Sir, this is regarding a little physics related. So when the cell started rolling, then how did it stop?
So it is having these receptors on the each of these cells. They have receptors on the surface which are able to attach to the vessel wall. So it is like hooks, basically. These hooks are attached, and then because of force, the shear force, they break also. So this and it's a small number of these bonds forming and breaking, and because of that you see the stop and go motion. So we had a stochastic model for the receptor ligand bond formation. Yeah. All right, thanks.
Okay, thanks a lot, Professor Samir. Thanks for the talk. So we have a small memento for you. Professor Chandan, could you please hand it over? Or maybe Professor Manasmita, you can just gift him the token. It's a memento for. Pleasure. Yeah, thanks a lot. So we can go ahead with the next talk by Professor Partha Goswami from Chemical Engineering Department, IIT Bombay. And after that, we will go ahead with the panel discussion.
So thank you, Pal ma'am and Habas Chandan, for inviting me. So today I am going to discuss something, a part of the PhD work of my student Siddhi. So this is work to understand how wake interacts with solid particles, but many of the things conceptually same as Professor Manasweta already discussed. So I am not going to the details of that, but why we are interested in this problem is any combustion system there will be some internals. Okay. Now if there is a fluid and some droplets, liquid droplets which are of micron size, and some solid products like ash and all these things, they will interact. In heat exchangers there will be exhaust gas, particle soutes and all these things. Even cyclone separator there will be an internal bodies. Okay. So then it is obvious that there will be wake generation and there will be interaction with the particle. This is a very recent literature from a paper that even coral reefs feeding depends on vortex generation and how this living substance come to that. And in natural phenomena, this coalescence of the drops and their growth sometimes depends on how large scale vortex are advecting them and the coalescence happens. There is an experiment where it shows that the wake particle interaction is really dominant in engineering system also. There will be a clustering of the particles, and in few places there will be no particles. Okay. And few of the recent work, as Professor Manasweta told, that we observed if particles are there in a turbulent flow, even at a very low volume fraction like 10⁻⁻³ there is a collapse of turbulence. That means even we think that the flow is turbulent, but we do not get any outcome of the turbulent flow like mixing or high rate of production or conversion and all these things. So the idea comes to our mind that can we not generate some periodical wake which will interact with base flow, which is not exactly parabolic but deformed parabolic, deformed profile due to the presence of the particle, and it generates turbulence. So that sometimes it inhibits the deposition, as Professor Bose told, or it gives higher amount of mixing. That is why first thing first we wanted to understand the phenomena of unsteady wake particle interaction. Now, here unsteady wake, and again this topic I have selected because OpenFOAM is related for that. Unsteady wake is generated by a cylinder, which is a very standard problem solved by the community, and here we have used body fitted mesh to generate the wakes. Okay. So, we are going to solve Navier-Stokes equation here. This is incompressible part, and there is one source term which is feedback force due to the presence of particle. That means, if particle is there in the fluid phase, there will be a drag force over the particle, and thus equivalent amount of force will be feedback to the fluid. That means, if I tell the term that it is a two-way coupled simulation, that means effect of fluid is there on the particle, and similarly a reverse force by the particle is also there on the fluid. That is one thing. The other thing is that in all the cases we have considered particle-particle and particle-wall interactions as well. Okay. So, this is a combination of OpenFOAM and LIGHTS. LIGHTS is a modified version of LAMP software which deals with solid body interaction, and we are solving this for a smooth particle to make the system simpler, and we are doing a hard sphere limit. That means, if particle comes together, collide, and they will rebound. We have not considered lubrication force because it is a solid or particle gas system. That means, there will be a lubrication rupture if particle inertia is high. So, they will really physically collide, and that we have observed in experimentally also with the setup what Professor Bose has already shown. So, this is my Maxi relay equation. It is little complicated equation, but this part is like our conventional Stokes drag law. If particle Reynolds number is low, then we can use this. Otherwise, there will be a modified Seeler-Neumann drag law. Okay. Now, there is another term which is the gravity term, and the other terms are negligible for high solid to fluid density ratio like Bassett force, which is nothing but the unsteady boundary layer formation, effect of unsteady boundary layer formation, and fluid acceleration and all these things. This term we can really neglect for high density ratio. Okay. So, we are basically solving these two equations parallelly, and sometime we are neglecting the feedback force, that is called one-way coupling. Literature is in literature we generally encounter the published paper which are dealing such problem with one-way coupling. But today I am going to show you that two-way coupling is very, very important even at a volume fraction of 10 power minus 4 minus 5. Okay. So, the simplified version of the particle equation I can write in terms of two non-dimensional numbers. One is the Stokes number, which is nothing but the ratio of particle inertial relaxation time to the fluid relaxation time. Here, since it is a cylinder wave problem, cylinder diameter is the length scale and velocity is the velocity scale. So, then L by U, diameter by velocity, is my time scale for the fluid. If I take that, Stokes number appears, and this is fluid number. So, that means it is the fluid inertia by gravity. Now, if gravity is 0, that means fluid number is infinity. Okay. And another interesting fact is that if I take the ratio of Stokes number to fluid number square, it will give me the terminal velocity. That means that ratio will dictate what is the relative velocity between the particle and the fluid. This is very important. So, there are few groups working in this area, wake particle interaction, like Professor Rama Govindrajan's group, Anubhav Roy's group, but they are looking at a different regime where Stokes number is very low or the density ratio is of the order of 1, though that fluid dynamics is very different in that regime. And here my system is like that, cylinder is there, particle, fluid both are falling downward, there will be wake generation. As a first step, we did not put any wall, because then it will be little complicated. As a combination of internal and external flows, other time scale and length scale will appear. So, here we are giving a free slip fluid velocity condition, but over the cylinder it is no slip condition. Okay. And we have to work with the exit boundary condition little rigorously, because otherwise when the heavy particle falls there will be a reverse drop. If we cannot do a proper boundary condition, then that physical phenomena will not be captured properly. Okay. Now what happens? This is a very common picture, vortex shading. We are keeping the Reynolds number 100 to 200. This range is laminar, unsteady. The word DNS I have used to indicate that we can extend this solver to a turbulent regime also without using any other models. Okay, it's just a Navier-Stokes solution. Okay. Now we have validated it with the literature, only single phase flow. Self similarity is satisfied, little away from the cylinder, but very near the cylinder there will be a deviation. And here these things are fluctuation, but these are not the turbulence fluctuation. This is basically unsteadiness. Okay, UU dash for the fluid phase. Now let us check what happens if it is a suspension. So there are two figures, one is little enlarged, other is original. So particles are coming close together. This is the path line of the particles. Okay, sometime they may interact or they may not interact depending on the inertia. They are flowing, but since it is path line, sometime their velocity will be accelerated if they come within the in the same direction with the wake direction. Okay, and if it goes in the reverse direction, their velocity will be decelerated. So this is one thing, but another interesting thing I want to pay your attention is that particles are jumping, correct? That means that particle cylinder interaction is creating one high concentration of the particle layer surrounding to the cylinder. Okay, I will come back to that point later, but this figure indicates that there is clustering, okay, and preferential clustering. Now we will try to understand that phenomena. So this is the observation I have already stated, but now we want to quantify the clustering. The question is how to quantify the clustering. There are different ways to quantify clustering. You can take small cells and find out the number of particles there at different places, but the problem is that very simple thing is limited by what should be the box size, length scale of the box. It is limited by the length scale of the box, and if your box size choice is not proper, then you will get different results. It will be very difficult to explain those. We have considered Voronoi tessellation. Okay, what is Voronoi? That means the plane, if we take a plane, then we will split it with n number of cells. Those are convex polygons. That means within a cell, if you take two lines, that lines, if you 2 points, if you join 2 points by a line, it will not cross the other cell. That is the simple thing of convex polygon, and each polygon will contain one particle. Every particle surrounding to every one particle there will be a cell. So these are Voronoi cell, and any point within that cell, if you connect it, it will be closer compared to any other particle. Okay, so within a cell of this Voronoi, which particle is there, if you take a point, collect the distance from this point to the particle, it will be minimum compared to the particle in the other cell. That is the idea of the Voronoi. We do this and it gives me the idea that how the size of the cells are. Now I got Voronoi cells, but that does not mean that those particles are forming the cluster or not. They can be closely associated, but it may not go to the cluster. How to identify the cluster? We consider a random distribution. This is standard in the literature, comparing with the Poisson distribution. Here we did not put much attention. It is proved that in random distribution comes as a Poisson distribution for particle. Now if we compare with the Poisson distribution, our distribution, then one part, this is area of the Voronoi cell. That means inverse of the area is my concentration. So low area means high concentration. If the probability is higher, there is a intersection point. If the probability is higher, that means this zone is the clustered zone, and if it is on the higher side of the area, that means lower side of the concentration, this is void zone. So keep in mind two parameters, one is AC, below that it is the cluster, beyond that it is void. Okay. So, based on that, once we get the distribution of the particles, we can estimate whether those particles are going to form the cluster or not. Now, what is the fundamental behind that? So, it is something like particle is moving with the fluid streamline. If particle Stokes number is low, it will be observed, it is moving, and if it is very low, that means it is a passive tracer like a fluid particle, it will move with the streamline. But in the other case, what may happen is my streamline and the particle is coming, it is being thrown out. Okay. If the Stokes number is high, it will not interact, it will move in its path. Now, to find out whether it will interact with the wake and it will be influenced by the wake, it can be calculated individually if we know the curvature of the streamline, because the flow is not turbulent. So, there will be a well defined streamline. If we know the curvature and the centripetal acceleration of the particle, then we can calculate whether it will come or it will be thrown out. But throwing out does not mean that it is being clustered somewhere. We cannot do that analysis for large number of particles. Okay. So, one conventional way of doing is that if you express your particle velocity, if you do an expansion over the fluid velocity plus Stokes number dependence, and if you put it in particle equation of motion maximally, then we will get the divergence of the particle velocity in terms of Stokes number and strain rate tensor and vorticity tensor. So, what is the meaning of divergence? If this quantity is negative, that means particles are coming close together. That means there is a chance that they will form the cluster. That is the significance of negative divergence. So, that means if you take the negative sign inside, it is vorticity square minus strain rate square. So, if strain rate square is high compared to vorticity square, that means it will be negative. So, the particle will be clustered in the straining zone compared to the vertical zone. We perform this analysis, and for single particle, first we tried to understand whether gravity is having any role. We found yes, gravity is very important. In the absence of gravity, that means Froude number tends to infinity. In the presence means unity. So, if we compare these two things, in presence of gravity, the behind void zone is being extended, particles are flowing down, okay? Because there are two forces. One is the wake induced flow of the particle, which is deviating from its vertical trajectories, other is the vertical acceleration. Okay? So, it is an interplay between these two. Some single particle calculation shows that there is an effect. Okay? So, here if you see the effect is very clear, in presence of gravity they are falling down. Okay? Now, coming back to the clustering. So, what we observed that in the absence of gravity, Froude number infinity, if my Stokes number, that expansion is valid till Stokes number 1, because it is a perturbative expansion. So, now if Froude number is of the order of is infinity, that means no gravity case, there is a clear leaf like structure of the void zone. Okay? And if we try to track the particle and the strain rate tensor or the skew criteria, what is the criteria I told earlier, then we will find that everything is being clustered in the negative zone. And this part is the cluster, this part is the void, but the particle location is highly correlated with negative Q. So, that is proved. Maybe 5 minutes I am having, I do not know. 4, 5 probably I have started, I do not know. Okay, fine. So, leaf like structure is established. If I go further, Froude 1, that means if I switch on the gravity, it is being transformed to a snake like structure. So, there is a change in the pattern of this void zone. Okay? That is because particles have now started to fall downwards and interaction with the wake is being minimized. Here also it is proved that, see, blue line, now red dots are coming. That means particles are being decorrelated with the Q criteria. They are going to higher vorticity zone also, and that is happening because the gravity is trying to play the role. Okay? So, here we have increased the Stokes number. With increasing Stokes number, but Froude is infinity means gravity is 0, still leaf like structure is there in the downstream, because here effect of vorticity decreases. Okay? But snake like structure is there just behind that, but correlation becomes very poor. Okay. Their correlation is lost because inertia, particle inertia is high and Froude number is of the order of 1. So, with that we have consolidated this thing, that the purple color which is q greater than 0. So, that increases if we increase the Stokes number or particle concentration, particle mass loading. Okay. These two things influence this correlation highly, and here is the boson. So, what I have shown earlier, that particles are being dispersed, that forms a high concentration zone surrounding this. So, this clustering is wake induced clustering, here this clustering is boson induced clustering. Two types of clustering happens here. Okay. Now, this boson clustering, the fluid is incompressible. Now, if it is a shock, that means it is showing some compressible behavior. So, we search granular literature. Actually, speed of the sound in the granular media, discrete granular media, is much lower than in air. So, the granular media can behave as a compressible media. Okay. That means the Mach number becomes high in the discrete phase, though the fluid, background fluid is incompressible. So, boson generation is possible, that is what it is. And here we found that if Stokes number is high, particle impact on the cylinder is high, they are being dispersed far away. That is why the radius or the curvature, radius of curvature is increasing for high Stokes number in the presence of gravity. Okay, because the inertia increases and they strike hard to the cylinder. This is the last slide. Whatever results I have shown you is mostly one-way coupling, and that is few are also reported in the literature, one-way coupling, but in the absence of gravity. They are trying to understand the geophysical flows, we are trying to understand engineering problems. So, we have demonstrated that gravity is having enormous role. Beyond that, what we have proved here, see the volume fraction is very low here, 10 power minus 4 minus 5, but still the vortex core are being dispersed in presence of particle. This is not, this is the vortex core at very dilute regime, this is the vortex core, Stokes number 1 is being dispersed. That means feedback force of the particle is very important, it changes the dynamics. So, whole lot of calculations we have done two-way coupling with different Stokes number and all these things. Okay, now, this is another scenario, Stokes 6. So, Stokes 1 RE, Reynolds number based on cylinder, is not affected much, that is the red color. But if we go for Stokes 6, there RE 200 also being affected, the last one. Okay. So, and there is a drag reduction. If we consider the drag induced by the fluid on the cylinder, we find that there is a proper signature of the drag reduction, because the change in the background wake. So, pressure coefficient changes. Okay. But one thing we have still not considered, because that is very rare events, the particle will give an impact in presence of gravity on the cylinder. But since it is a DEM code, that means particle will be having a finite contact time with the cylinder. Okay. So, it is very difficult to calculate the momentum transfer by the particle. That is why I have written that drag reduction by the gas phase. Okay. With that, I acknowledge the lab scale cluster developed by ACRB DST Fund and IIT Bombay Supercomputing Facility, and thank you for your patience.
Thank you so much, Professor Partha. Any questions for Professor Partha?
On these particles, instead of having empirical drag forces, can we not integrate the surface forces?
These particles are very small. My plan is to go to turbulent regime.
Right.
So, then their size is much smaller than the Kolmogorov size,
I see.
Kolmogorov scale. That means they can be considered as a point particle. Now, thing is that in other work, like where we have seen the turbulence collapse and all these things, we have done some multiple expansion.
I see.
That does not, so point particle is good enough approximation. The other thing is that this Seeler-Neumann is a correlation basically, and this correlation is developed for a steady state. Okay. But the thing is that our particle Reynolds number, small particle Reynolds number is of the order of 10 or less. So then there is no unsteadiness comes. Some fluctuation will come, that actually in Stokes law or whatever law we use, we should consider the relative velocity between fluid and particle. Now fluid velocity should not be polluted by the disturbance of that particle. We can consider the disturbance by other particle, but the particle on which I am calculating the drag, I should not consider the disturbance. So that disturbance is corrected here. Okay. So other unsteadiness is not.
Thank you so much.
Yeah.
So I would request Professor Janani to please come here and present a memento to Professor Partha.
Thank you.
Thank you so much, ma'am. So with this, we conclude the talk sessions and we will go ahead with the panel discussion. So we have the faculty partners who work with the FOSSEE team and advisory board members of CFD FOSSEE team who will be joining, who are there online. So Deepa, could you please bring them on the screen? Okay, so we also have Professor Amol Subedar and as panelists, so Professor Samir and Professor Shiva, could you please come here and sit? Because then we will have a face-to-face discussion.
Yeah. I have to take my charger also.
To you. All right, so so basically this is very informal, and thanks for those online who are our faculty partners and industry advisory board members they joined. Apologies for a bit of messy configuration, but I think the interesting part would be to hear also some of your response, but I will start with discussing who are presently here. So basically I have chosen two of the interesting questions that are in my mind, and I wanted to basically trigger this conversation so that we can keep thinking about it also from the FOSSEE perspective. So one of the things that I thought is basically how we are seeing the positive part of ML and AI techniques and how we want to embrace them towards our approach of developing open source codes, keeping apart the negative sides of it. But I think in my opinion there are also some positive aspects of it, particularly using LLMs for automotive mesh generation, etc. So, and the second part, I think depending on time, the second part is, of course, we are all discussing from morning that we have to go towards GPU acceleration because of facilities and other things. So how do we want to see it in that respect? So I think I will start from the first topic, that I think we all here use OpenFOAM, kind of I'm keeping OpenFOAM as a benchmark thing, but of course it applies to any of the open source code. So Professor Janani, what do you think, like in terms of accepting ML or AI techniques, what do you think is your opinion towards open source codes?
Okay. So the answer is very obvious. I think they have a huge role to play. Okay, but the important thing, not the negative aspect, but the important thing to keep in mind, because one of the courses that I was doing, I was trying to kind of sensitize students on dual application, may it be methodology development, numerical methodology development. The thought process, perception of AI and ML is, take a bunch of data, put it through and generate a correlation, a regression analysis, which it should not be as far as CFD is concerned. It should actually go beyond that, right? And I think there's huge scope for, tapping that energy into, generating something which is both on the numerical side, the GPU side, as well as the application side. What I find is very few people who are actually tapping it at the right places. And open source software, all OpenFOAM codes or open source codes, I think with OpenFOAM the challenge is it's in a set environment and you need to work within that. So I think a lot of I think Shiva is training quite many students in that direction. But other than that, I feel a large amount of students just use it as a black box still. And I hope for it to be, something beyond that.
Yeah, towards that, if I can go to Professor Shiva, that I mean, even towards learning the underlying codes or the source code or to understand, do you think LLMs have a role to play or can be used positively to understand the source code?
Okay, let me tell you my exact view on this, and I have been sort of actively using machine learning in development for OpenFOAM. Okay, so there are two ways you can use machine learning. One, which Janani highlighted, the fact that you can actually use ML, take the raw data, etc., train the ML algorithms, and solve the fluid mechanics problem directly on it. That's one way of going. I'm not talking about that. I'm still talking about using conventional CFD code to do your simulations, to do your engineering calculations. But here is where ML comes into play. When we look at codes like OpenFOAM, which are highly customizable, highly modifiable to the kind of problems that you want to do, ML actually plays a fantastic assistant.
Yes.
Okay, so let me tell you that I have cut down my development time of OpenFOAM itself cuts your development time down, right? So I touched upon it early in the morning when I said that, I took a problem, it took me 3.5, 4 years, what would have taken me 10 years if I had to write a code from scratch. Today that cycle time from 3.5, 4 years has even come down even further down, because I can now code parts of OpenFOAM using ML, okay? That does not mean that I trust it completely, but my effort sort of significantly reduces. Now, the philosophical question there will be like, what's the learning are you getting? Are the students really learning if I go and tell the code, hey, write a solver for me using this PD? I can do that today, right? I can pull out a PD from a paper, feed it to something like Claude and say, write an OpenFOAM solver for me. And then you will question, what did the student learn? My point is, we have to take the level of abstractions to higher and higher levels. If I say, if I go 10 years back, I'll say even OpenFOAM is sort of cheating, right? You're not writing the baseline code. You're just doing FVM : and divergence of thing. You're not writing the divergence operator. You're just putting the divergence operator. You're trusting the divergence operator which is there. Let's say that you write, you are enthusiastic enough to write the divergence operator. Okay, but you're writing a higher level C code. You're not writing the assembly code. What level of the rabbit hole do we go down to, right? So that's how I see. So we have to sort of abstract. So that's the entire essence of any endeavor. You want to abstract the things out so that you can do the higher level science. So today we are at a stage where we can tell, go into an AI platform like Claude or whatever it is and say, I'm going to train you on all the versions of OpenFOAM which have been existed, right from version 1 to version 2506 or 2512, whatever has come out, and say, now I want to develop a certain solver, I'll put in things. But I need to understand the fact that, hey, it can make mistakes and I have to go and sort of verify. It's a trust but verify sort of thing.
No, I
right?
completely agree. I think
so
we
that's
need
what
to
I'm trying to say.
understand
You
what
need to
we
understand
are
what you're
getting
doing,
out
and
of LLM model.
you need to be able to verify that what you're doing is correct, but that's supremely accelerates your development time. Just to add weight to what I just said, just in 2 months period, I have developed a porous media two-phase flow solver from so-called scratch in OpenFOAM with the help of LLMs. One person doing it, that's it. I've been able to put in porous media correlations, model two-phase flow, all this just because of LLMs. Yeah, it did not get it right the first time. I had to struggle with it a lot, but hey, what would have taken me 3 years is now taking me 2 months, and that's great.
Yeah, I think the point lies there that how do we use these LLMs and how do we verify the output. So the other parts, if I go to Professor Partha, that what do you think like this makes a difference for open source code and all the so-called conventional in-house codes, right? So do you think there are still some groups who still trust in-house code and it's conventional, but do you think these kind of techniques will encourage them to make those codes more updated and release them as open source code? I mean, this is another thing that why OpenFOAM should only be the one code which people know. I mean, of course, in India, I think every research group, CFD research group, they have their own code which is developed. So why not we, take it to the next level and make it open source? So, and do you think with the power of these kind of LLM models that can encourage some of these researchers?
Nice point. So I'll split your question in 2 parts. One is that advantage of using open source code over the in-house code. So it is not always advantageous to use open source codes if the in-house code is developed by the user or associated users with a long time. But sometimes the thing is that suppose I am having one in-house code. Now I am trying to migrate to OpenFOAM for few of the problems. Okay, the idea is that students training on OpenFOAM will help them much more in future than their association with my in-house code. That is the first thing.
In terms of employability.
Employability. Oh, that is also a very important part nowadays. Okay, so because that is the main driving force even for PhD students. So that is one part. The other thing is that sometimes some limitations will be there in in-house solver development. Like the way OpenFOAM is parallelized, my in-house code is not. Now the point is that whether I will devote time to make it parallel or I will try to extend its capability or try to understand the physics. Okay. So that is the question always there for in-house codes, and taking one in-house codes developed in one lab individually is very difficult to bring to the level of OpenFOAM because now user community is very high.
Yes.
Okay, so I feel, in my opinion, if we have to use open source code, OpenFOAM probably is the best platform. Okay, that is your first question.
Yeah, I think, yeah, please.
Okay,
I mean,
and I am always in favor of using LLM and completely agree with Siva. Okay, so thing is that now learning curve is very steep. Actually, threshold of starting research has increased enormously. Okay, now if I tell that I am solving one Stokes flow problem, no one cares. what is there. So now I have to start to publish or to address industrial problem, then I have to reach to a level.
Exactly.
Okay. And to reach that level, I think LLM based solution is probably important for OpenFOAM, because last 4-5 years.
I think I completely agree. I mean, I think the complexity of the problems in today's date is an important parameter, that how translatable it is to either industry or practical application. Although, you know, the reserved mind always say, okay, why don't we solve the flow past a cylinder first by our writing our own code, because we will then understand what is a second order accuracy, for example, which we might not realize while using OpenFOAM.
That. For that, some sort of basic training probably will be
but I think, yeah, there has to be a balance, in my opinion. Of course, when a student is learning CFD, they needs to write, at least solve a diffusion equation by writing the hard code. But when we are doing real life problem, I think a PhD in India is, let's say, 5 years. It's not good enough for writing a code from scratch. In other countries, in the UK or France, let's say 3 to 3.5 years, we cannot even think about it, that a student will write. And point is, why to reinvent the wheel? I mean, a Navier-Stokes solver, it takes 5 years to write, just a Navier-Stokes solver. Then we are going for coupling and other things. So I completely agree with it, but I think the balance, and in terms of the way, another point is why in-house codes are difficult, in my opinion. I mean, when I wrote a code also in my PhD, the main problem is documentation, right? We don't comment the code, we don't follow the research software engineering practices, because we are not software engineers, we are not interested, we are only interested about the physics, what we get. So in that way also, I think LLMs have a great role to play, because if we write a code and give LLM and tell that, okay, can you make an automatic documentation? I mean, we can link it to GitHub workflow and make a HTML website for it automatically, which can then immediately put all the documentation as a website format, and which can happen, I think, in minutes, right? So that's where probably even the learning curve, you said, the learning curve of OpenFOAM puts many students off, but I think, why not we tell LLM, just I don't understand this, what is it actually doing in C++, what kind of class and objects it's using. So I am for it, but again, I'm from a more later generation, so I want to basically, I have also heard a lot of reserved opinion about it, about, again, why not we solve a flow faster cylinder. So I will go to both of you. Do you have to add, I mean, do you have anything to add to this discussion, that should we actively, you know, promote the new generation of students to use LLMs, or how do we make this balance?
So yeah, if I understand correctly, LLM you can use for writing codes, or in fact not even using OpenFOAM, but physics informed models, right? So that is something.
That's another class of things, but yeah.
For writing, surely yes, it is really helpful. And the only thing is that if you know how to check with, let's say, any LLM, that if it is doing the job correctly or not. If you have 10 or 20 test cases in mind, after 20, if you are setting 20 test cases, I'm sure that it will get it right. It never gets even simple things right in the first attempt, but with some test cases, it does the job nicely. So surely it is really helpful, no doubt about that. You can use any so any AI tools you can use. It will write an at least the structure will be nice. In fact, I have learned many good practices in terms of even memory storage, right? When to clear the memory and so on. So I code in C++. Many things I missed, but if I ask now ChatGPT, please write a code for me. Some things I have learned really from that part. So in that respect, it is really helpful, because as you said, we are not trained high performance computing people, right? So by training, we are let's say engineers from different backgrounds who are writing codes when the need arises. So yeah, so that's what.
Professor Sami, do you want to add anything?
Yes. So from the first question, whether OpenFOAM should be used, I mean, even if you're using commercial software, the idea is, of course, a shorter time to learn, and secondly, the diversity of problems you can solve. That is usually a limitation in in-house codes. So definitely helps to have OpenFOAM. And then the other thing about using LLMs, the idea is how much it is exposed to OpenFOAM. The more it is exposed, the more useful it will become. So those are the
I mean, of course, I mean, if it would have been possible, we would have tell the make OpenFOAM GPU scalable, right? We could directly use it for GPUs, but it cannot. We have to do the coding. We have to port every library of OpenFOAM to GPU. So LLM cannot do it. So do you want to add anything?
Yeah, the metaphor I would like to add is that, you know, my father was an engineer. So when he was an engineering student, he used something called as a slide rule for calculation. We all learnt logs using the log table books when we were in school, but nobody uses that anymore. But we understand the principles of it. We don't even use scientific calculators as much anymore. I force my students to use scientific calculators. But the point is, what we see is we are seeing an evolution of a tool, right? The thing is that you're able to do more and more complex calculations, from slide rules to scientific calculators or whatever it is. I think LLM is just another path over there. That's about it. So we have to see it and the fact that we should harness the opportunity that we are able to solve more complex problems because now we have better tools and we're not stuck at the basic level. That's all I would see.
Okay. So I think I will go to the online participants, and I cannot see all of your names, plus can you please unmute yourself and share your experience in your institutions, if you have, and what's your opinion regarding this. Can you one by one give your opinions, please, if you have any.
Yeah, hi, Professor Chandan and all other participants. I'm Divyesh.
Yes, Divyesh, please go ahead.
Yeah, so since we are talking about AI and ML, so I remember a few years back, even industries were very hesitant of using OpenFOAM because of the time that it takes to just build one test case setup, right? But because of the AI tools that we have right now, so let's say if it was taking 3 to 4 days to just build one case setup, now you can do that same job within minutes, right? So that is one very basic thing that students can learn, and even industries these days I'm seeing a lot of people are using AI that way, but I think there's more to that. So
so yeah, in my opinion, so when I tried setting up cases directly by LLMs, it cannot do it at this stage. Even last week I tried, it cannot do it. Particularly for stationary simple problem, it can probably do it, but complex problem it cannot. But it can give us, in my opinion, it gives us the structure. That okay,
yes,
so
exactly,
this is the script that you need to modify to adapt to your problem, which probably previously we had to go to a tutorial, then understand how the tutorial is done and then adapt it. Now we can get a structure, and then if I know already OpenFOAM, I can understand how to modify it. So that probably, but again it is getting exposed more and more, so probably with time it will be more accurate. Thanks, Divyesh. Yeah, please. Yeah, please carry on.
Yeah, so that way we are using these AI tools to get more get things done more faster way. But see, there are two types of industries, right? One is manufacturing oriented. There you need to simulate problems in a rapid basis, right? So you don't have much time. Let's say you don't even have 1 week to solve the problem and then go with the solution or go with the trial. So in these cases, I think this sort of conventional approaches are well good enough. But there are industries, for example, I remember Pandu is doing a really good job. There I think LLM and AI can be used. I think they are already doing it. So where you have more towards like very focused problem and very focused industry and very focused physics that you want to solve a very particular problem that you want to solve, then I think we can put more efforts and then create this sort of codes.
Right. I see that Manav, are you there? Dr. Manavendra Dev from NAL is there. So I would like to know.
I'm here.
I would like to know what is this perception in national labs. What do you think within NAL? What kind of practices currently you are adapting to?
So good evening, everybody. Let me first thank all the organizers for such an excellent day. I feel I'm still a student only after hearing all the professors and still learning. So yeah, from the a lab like National Aerospace Lab, we are more into trying to bridge the valley of death in terms of this knowledge. So we have different groups who will be working on say in-house codes, and then we have a group which works with the open source platforms like OpenFOAM as well as SU2, and we also have groups who use the commercial packages like Fluent and the others offered by say Dassault and all. So our experience has been like on case to case basis, each one of them will be quite unique. So from that perspective, when we look into say a specific case of OpenFOAM, initially we had been using it for our flagship programs of SARAS for understanding the fluid dynamics of that. And then we found that as some of the speakers have also mentioned that the ease with which one can use it, and that's one of the reason I think you have embarked on the GUI part of it, which makes it more user friendly. Probably due to that reason, and also because of the slightly complicated structure. I won't say, I mean, those who are working with OpenFOAM will not feel it, but if you compare that with SU2, in SU2 you are only having the configuration file, which has all those information which in OpenFOAM has in various directories. So then somewhere when we had to compete with time, and there was not much space given to us for exploring or having a liberty of time, we had to switch from one open source to another open source because of the relative advantages of that. So that is one thing which we got feedback from our team. Of course, AIML is happening today, and we are looking at various ways in which AIML has been used, and CFD community looks into that, like surrogate model or reduced order model. But what excited me more is the two things. I would like to borrow the words from the first two panelists who spoke about, the AIML model should not be basically, replacing a RANS solver. And then the level of abstraction also needs to be slightly higher. So I would just refer to our Heisenberg's, statement. When I meet God, I'm going to ask him two questions: why relativity and why turbulence? And I really believe that he will answer for the first one. Now, for the CFD community, turbulence is still an unanswered question. And one of the ways in which the AIML is looked upon, I mean, this is again my only reading of the literature, is that for developing more accurate and efficient RANS models, again, the research community is looking to the the AIMLs for by using the DNS data, and then trying to figure out whether those coefficients which we use for our RANS modelings, whether they can be improved or whether there can be a continuous improvement. So this, I think, will be something which we at NAL will also try to look into. Of course, that is the way in which we have this perception towards AIML. We have there's no doubt about using the open source tools, various reasons. And yes, coding, I think all the panelists have shared their views, so it really helps speed up the learning curve. So I also have examples where not OpenFOAM, but the intern within 1 month, he was able to write a code for integrating OpenVSP's output within the FreeCAD framework onto, using it to apply the aerodynamic forces onto a structural model. using calculix. So there he used LLMs. He took the initial help from LLM, generated a code which could interface the two open source softwares, and within a third open source framework, he was able to do it within a short span of time. So definitely, while AI/ML is helping the learning curve, I think from research perspective, we are looking more into raising the level of abstraction higher and looking whether the turbulence models can be improved using the AI/ML. So that will be my submission.
Thanks, Manav. So I think since you have brought up the neural network aspect, so that's another very different branch of AI and ML. So apart from LLM, so I just, for the sake of time, I think we need to close this discussion. So I'm not bringing up the GPU thing, but just I want to say that the panelists here present, what's your opinion about two things? Of course, we use neural network for CFD perspective. One is, of course, the way Dr. Day told that we find out model parameters, more better model parameters, like RANS is one particular application which has attracted a lot of literature, and I would say that it's quite good. I mean, because RANS modeling is like cooking, I think. The more spices, the more better model parameters you get, the more better results you will get. But apart from that, the other branches which actually made a lot of, I would say, hype in the past 5 years is PINN, or physics informed neural networks. But in my opinion, when I still see literatures, they are limited to very fundamental problems. I mean, maximum flow around a cylinder and comparison with that. So maybe whoever I think you have experience with, can you add what's your opinion about this kind of neural network based models such as pins and other things in terms of accelerating CFD? So the other application probably of neural networks is to accelerate by surrogate models. So yeah.
So in my opinion, pins are useful. What are pins? Essentially are nothing but optimizers.
Yeah.
If you look at any sort of neural network that works, I mean, you might say it's some n layer with 25 neurons or 30 neurons or whatever. Basically, you just have a bunch of weights which you're optimizing to look at the output. You're minimizing the loss function. So I see it as an optimization problem. It's just that the optimization parameters are very large, and you're able to run it over larger and larger data sets. Now, if you're going to ask me how is it going to help in physics-informed neural networks, yeah, it will help in certain closures. It'll help in, so this is the spectrum that we have, right? The spectrum that we have is that A, we have either lots and lots of data, then we can just do raw interpolation. That's what it is, right? Or we are at the other end where there is very, very less or no data. But usually the story is somewhere in between, where we have little amount of data, but we also have some amount of intuition on how things work. What is that intuition? That intuition is, oh yeah, it obeys something like Navier-Stokes. It obeys Newton's second law of motion. We have that intuition, right? So we are mixing our intuition with these closures, right? So that's where the story comes in. Now, the question is, how strong and how good is your intuition, and in what realm does it work, right? So if I'm going to now look at only laminar flows, if I'm looking at creeping flows, if I'm looking at extremely low Reynolds number flows, do I really need to go to a pin? No, I don't. Because I understand this phenomena fairly well, right? Now, if I go down to the molecular level, maybe I do not understand it as much. But in the bulk phase, I really understand it very well. It's like saying that I understand V is equal to U plus AT, right? If I want to do calculation of the trajectory of a projectile, I'm not going to use a pin ever. I know V is equal to U plus AT. I can do all these calculations with a very good engineering, error assumption, right? So the question is, you have to pick that problem. Now, where the turbulence is important, where the transition takes place. Okay, turbulence is one place. Where is that? Let's say, okay, I have, phase transition of a particular fluid whose property state space I do not know properly, right? Water is very well studied. Basically, I come up with some other fluid whose state space I do not know properly. This is where pins, etc., will help with reasonably accurate data. Now, I will always go back to one quote which I heard when I was a young researcher in CFD, is that nobody believes the modeler except the modeler himself. Everybody believes the experimentalist except the experimentalist himself. The reason is because the experimentalist knows what errors are there. We all are super confident about experimental data. Do we know what the error bars are there? What is the error in the measurement?
That's true.
So you have to add all these pinches of salt when you are doing pins, because pin is again training on this experimental data, right? So you have to add this pinch of salt. That's my take on it.
All right.
I'm not dissing any experimentalists. I have huge respect for them, by the way.
My exposure is very limited on pin, so I cannot make much more comment. But what I think in few of the cases like chaotic flows and all these things where we have limited data and little bit of understanding, probably pin can take over. But in case of all this fluid mechanics problem where the data is, we have very limited data in true sense. Okay, so probably then pin could be good choice.
Yeah, but problem is again, I mean, my point is there are a lot of literature in current days where we do CFD simulation to train that pin to compare with that simulation.
Yeah, that is
so what is the cost of training and how much training
so
we need?
90% data is being used to train.
So why don't we do the simulation directly then? I mean, rather than training it. So yeah, anyway, I mean, this is, but there are, I think IC pin is very good useful tool for reduced order modeling. So previously reduced order modeling was based on mostly decomposition, either POD based, projection based, but nowadays we can, if we have sufficient data, we can get some reasonably accurate reduced order model using these surrogate modeling techniques. And not only pins, there are different class of surrogate modeling techniques, which I have seen is quite useful in aeroelastic analysis. Particularly in my field, I have seen quite nice data which industries can use and directly in low order model in that sense. Okay, I think we are running out of time. So can I, before we close, can I request all the online, our faculty partners and our other connections, please can you briefly introduce yourself so that the IITB community knows how. Okay, Hari, you can go ahead, please.
Yes, are you able to hear me?
Yes.
Are you able to hear me now?
Yes, we can hear you.
Yes, thank you very much. So myself, Dr. Hari Krishnas, I'm a faculty in the Department of Mechanical Engineering, Kochi University of Science and Technology, Kochi, Kerala. And I completed my PhD from IIT Madras in 2019. So I was working in OpenFOAM for almost 10 years, more than 10 years, with various topics, single phase flow, heat transfer, multi-phase flow also. I started associating with FOSSEE in 2019 onwards as a student. Then as a faculty also, I was delivering lectures during the workshops. I was mentoring students also. So regarding the topic of discussion today, so one of the main important parameters, especially when we consider AI, ML and all, quality of data. You might have seen, we all might have seen Gemini, when we type something, they always say Gemini can make mistakes. So if you are giving garbage in, obviously garbage out will be coming. So the quality of data entering into the LLM models or AML models is very, very important. So we need to make sure, if you talk about FOSSEE or contribution from FOSSEE, we can say that, as a simple example, I can give you like, if you see the official user guide of OpenFOAM, it is only 200 plus pages. But if you see ANSYS Fluent, it is around 5,000 plus pages. So there itself you can find the difference. So if you have a trusted data or reliable data for training, obviously that will be very, very helpful for LLM or AML, application of AML for accelerating the use of OpenFOAM. So in that scenario, FOSSEE can significantly contribute. That is one point. And another point I just wanted to say, as Microsoft named their AI agent as Copilot, as the name indicates, we should not make AI as a pilot, rather we should make it as a Copilot. This Copilot will help us to doing the activities, help us in doing the things much easier way, which is short period of time. So we should have our control, but Copilot or AI tools will be helping us to do the process in a very short period of time. So I can say in single sentence, AI will not replace CFD, but CFD without AI may soon be incomplete. That's what I feel.
Thanks, Sari. Yeah, I think it already syncs with all the views we have got. Yeah, can we just go back a very brief introduction with all our online participants, please?
Yeah, Hello, I'm audible.
Yes.
Yeah, so thank you, Dr. Chandan Bose, the IIT Bombay professors, and the FOSSEE team for organizing such a nice workshop. So I think in the last session, I have presented some AI/ML in CFD. Now, as many professors said, I totally agree with you. By the way, I'm from TCS Research Industry, so we are also working in the several areas. With OpenFOAM, the commercial softwares, and as Dr. Bose was mentioning, the pins and other things. So I would like to say that AI ML, yeah, nowadays it is a hot kind of hot cake. The funding is there, and the students are doing it for the placement and all. And as Dr. Janani said, it should not be kind of they are doing some rigorous analysis or using as a black box. People should know the mathematics behind it. So many people miss it. People know how to tune the model, but what to tune and how these mathematical formulations are coming, they do not know. And another thing I would like to add, for the reduced order models, let's say you are doing POD or DMD. So we did something with called neural network informed DMD or neural network informed POD and GAPI POD or GAPI DMD. So when you are having sparse data or the missing data, you can use that. So always what I experienced in my industry or with my employees and the students, that these neural networks or these AI ML models can always complement the CFD, but it can never replace the conventional methods or the conventional learning process. And even in the molecular dynamic simulations also, if you see, nowadays people are, although this is out of scope, but I want to mention that, as you know, these MD kind of simulations are very much time taking. So people are coming with the neural network informed or the ML informed algorithms to make faster the processes, the computational faster. So this is how the things are evolving. So finally, thank you all for giving me this opportunity. Probably whenever the next talk will be scheduled, I will present some of the latest techniques. Thank you.
Thanks, Arnab. I think Professor Dheeraj Garg has raised. Professor Garg, please go ahead.
Yeah, namaskar everyone, and thanks a lot for giving this opportunity to attend this. So my take on LLM and AI based is the problem I am facing in the CFD problems, and I think it would be nice if AI and all other these methods can be linked with the selection of proper initial solution. Sometimes initial solutions are very critical to get it converged. So if AI can be modeled to give some good initial solution to begin with, it can be used to give some good initial settings for the solvers to make it converge the problem. It can be used to, if it can be done in future, to give some good meshing, to improve the meshing according to the problem of physics or the situation, that it can lead to improved convergence. So it need not to replace the whole mathematical model, but there are certain areas where it can definitely contribute to give uh, and help in getting solution faster. And where I feel that if there is some help in that part, it can definitely improve in the getting output of CFD.
Thanks,
That
Professor
is my
Garg.
take.
Thank you. Nikhil, please go ahead.
Yes, hello everyone, good evening. I am Nikhil Bhamre and I am currently founder and CEO at CFD Baba Simulations Private Limited. So I completed my master's in thermal engineering, which is closely related to CFD. And then I worked for 8 years in industry as senior CFD engineer. And now I have started my own firm, CFD Baba Simulations Private Limited, and we provide CFD consultancy training, as well as we are developing our own CFD tool powered by OpenFOAM called CFD Forge, which will help us to reduce the case setup time of OpenFOAM cases by almost 60%. and it will also eliminate the steep learning curve of OpenFOAM.
All right.
So the work is currently ongoing, and the point of AI and ML is also very interesting, because in manufacturing industry, we need to run simulations very quickly for different designs to check which design is performing the best. For that, AI and ML can play important roles, is what I feel, towards which we can work.
Thanks, Nikhil.
Yes.
Pushkar, can you please introduce yourself briefly?
Hi, Chandan. Thanks for the invitation for this wonderful day. Actually, to be honest, I was working and in parallel listening. So yeah, only 50% attention span. But yeah, first of all, ground rules.
I think his connection is lost. Can we go to Tushar? Pushkar, can you hear us? Okay, Tushar,
Okay.
please go ahead. Actually, we are running out of time.
Yeah, so thank you, Professor Chandan Bose, and all the panel members out there. So I'm Dr. Tushar Chorishi. I did my PhD on non-equilibrium flows from Johnson National University in South Korea, where we actually made solvers, CFD solvers particularly.
Oh.
So there I worked on OpenFOAM for the flows, like for example, the non-Newtonian fluids, wherein the stability is an issue. So, I mean, with the kind of discussion which you elite people had, I was extremely sorry because I couldn't get the time, as I am working as an associate professor in MIT University Pune. So we had a faculty development program going on. So I just took some time out of it. So I couldn't hear, but yeah, some part which I heard is regarding the AI. So yeah, AI can assist in those areas particularly, because there are the limitation of numerical methods, and even the governing equations are also not maybe due to high elasticity. The governing equations are also not working as what is planned in the numerics. So there the people are struggling. So I hope that could be new thing which AI can do.
Thanks, sir.
Thank
So,
you.
Pushkar, can you hear us? Can you just briefly
Yeah,
introduce yourself?
am I audible?
Yes.
I'm sorry, I broke off there. So yeah, first of all, I was saying that I am not a researcher, and major priority for me is either helping on new product development or uh, working on some research project that might have gotten funding. Okay. And that is also very rare, working on a research project. So yeah, most of the time during execution, uh, companies don't want to work with a software that is open source, okay, and they would rely on commercial codes more. Hello, am I audible?
Yes, yes.
Yeah, so uh, uh, and the views of say the management on my side is we can use open source for some sort of iterative design work, but the final capping run has to be from commercial software. Also as far as maintainability of the knowledge, like the major question that my manager would ask is uh, you know uh, what will happen if you sort of are not with the organization, and who's going to learn OpenFOAM again. So yeah, all those questions are there. But yeah, I guess Chandan, you just asked us to introduce ourselves. I'm sorry I started speaking there, but yeah.
No, that's fine. Actually, we are actually running out of time. That's the
I'm
only
sorry.
reason.
Yeah. Thanks.
So, Dr. Reddy, can you introduce yourself?
Yeah. Hi, good evening, everyone. I'm Rajesh Reddy.
Assistant Professor, Shivanada University. I'm in Mechanical Department. PhD from IIT Hyderabad in Computational Fluid Dynamics. So as we are running short of time, I would like to stop here. Thank you.
Thanks, Dr. Reddy. So can I now hand over this to you, Professor Prabhu, just to thank everyone and close the.
Hi everyone. So I would like to thank on behalf of FOSSEE. So this workshop has been organized under FOSSEE. So first I'll have to thank all of the experts, both in person as well as online, who have taken the time to share their knowledge freely with everyone. Also need to thank the participants. I think there are some online, there are some in person. Yeah, that's fine. I know. That's okay. I understand. So, yeah. So thank those of you who are attending online as well as here. These events are meaningless without participants. So thank you for attending. And the FOSSEE team has actually put in a lot of work for this. So especially Professor Chandan and all the team. He's been mentoring the OpenFOAM side of things. We don't currently have a full-time faculty at IIT Bombay who's mentoring the OpenFOAM side, but Professor Chandan has been the one doing that. Earlier it was Professor Janani, and then before that it was Shiva. But right now he's kind of carrying the torch. And it's a lot of work. I mean, there are several people who work, so he has to work with them remote. Of course, we have Payal, who's our excellent manager for the FOSSEE, and she's been after me on book this room, get this done, and all of these things. So there's a lot of behind the scenes work that has gone into making this happen.
This concept was generated by Professor Janani. So
okay.
She wanted to connect all the people who are using OpenFOAM and working on CFD
right.
at IIT Bombay. Probably the groups don't know each other.
Correct.
They are not introduced to each other. So if we can generate a network of people who are working on or who are using OpenFOAM in their research, it will be great. So my effort was towards that one.
Right. Yeah. So just want to say that there's been a lot of work from the FOSSEE. I know because that part I do know about at this point. So thanks to them, and also thanks for all our supporting CD folks who are doing the recording and then eventually editing and all of that. But once again, thank you to all the experts, because I know how busy Shiva is in particular. I was in his footsteps. He was in his shoes a year ago. So, and I know all of them also have a lot of other engagements. And so thank you very much. It means a lot. And these kind of things will not happen without your support. Thank you. Yes, and so as a token of our appreciation, we're going to hand over this little memento to Professor Chandan. Thank you so much. Well, he's part of our team, but still. Professor Amol. Thank you. Huh?
So with this, we'll close the symposium, the day one of the symposium. Tomorrow we will have the workshop on advanced level of OpenFOAM. So I would call our senior manager, Ms.
There's one person we should thank.
Yes.
The Department of Aerospace Engineering.
Oh yes. So Usha will. So Usha will actually formally close the session of day one with the vote of thanks. So what to you, Usha?
So half of the vote of thanks already Professor Prabhu has done. So, but still I thank the experts and the professors at IIT Bombay who were with us from the morning onwards, and of course students, research scholars who were with us. And I would like to thank the OpenFOAM team who actually had put on a lot of work for coming up with this event, and Professor Jenny and Professor Chandan were always there for guidance and support. And I will also like to thank IIT Bombay for hosting us, and for sponsoring this particular venue. I thank the Aerospace Department of IIT Bombay. And this is a Ministry of Education funded project. So I thank the funding agency for supporting us for, it has been running for the past 15 years. So 16 years. So I thank them also. So thank you all for making this a great event, and do join us tomorrow also.